Oh, it's still spinning here. Now it says it's launched. C'est bon? Okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself. C'est bon? But now the okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself. C'est bon? C'est l'audio de iStream qui passe. Okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself. C'est bon? C'est l'audio de iStream qui passe. Okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself. C'est bon? C'est l'audio de iStream qui passe. Okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself. C'est bon? C'est l'audio de iStream qui passe. Okay, so now we're live. Oh, it's still spinning here. Now it says it's launched. Oh, but now I'm hearing myself.
Faut juste couper cette fenêtre. Faut pas que vous diffusiez.
Oh.
Faut couper tout YouTube. Coupez tout là. Ça va quand même tourner.
Ah, d'accord.
Enfin, fermer toutes les fenêtres de YouTube, c'est lui qui renvoie.
D'accord. Okay.
Avant, c'est bon.
Okay, I think we're good now. That's enough to make somebody go crazy to hear yourself multiple times in your... Okay, let's try again. I said this, let's go. Okay, so the slides will be available online for all the speakers that are in the room that haven't yet uploaded your slides. Please upload your slides. If you go to the CFP page where you submitted your talk, there'll be a section where you can upload your slides. I sent you all an email about that, so several of you have done it already, thank you, but they'll automatically show up in the schedule, so if you find the talk in the schedule, you can download slides from there. And then, yes, thanks to the Baylib staff for helping organize the event. If you see, we all have these shirts with staff on the back. If you have questions about logistics or anything like that, feel free to ask anybody with the staff shirts on to help out. Most of us are kind of engineers by day, so organizing an event is not our daily work, so be patient with us, but yeah, feel free to ask questions if you have them. We'll help with what we can. And then, yeah, if you are the social media type, feel free to spread the word about the event. And share your photos, share what you want, help spread the words about embedded recipes. I think that's it. It feels like I missed something, though, in the chaos. No? I think that's it. Okay. All right, let's go ahead and get started. I'll invite up our first speaker. Oh, yeah, we're going to have a mixture of kind of normal talks and lightning talks, so some 40-minute talks, some 15-minute talks. And in between, there'll be a little break, like a couple-minute breaks while we switch computers and change things around. Feel free to stand up and stretch your legs or move around a little bit as you need to, but the time between slots are fairly quick. But yeah, move around as you need to. And so, yeah, I'll invite up Paul for our first talk. And thank you all for coming once again.
this works. Cool. Good morning, people. Yeah, Kevin's promised you highly technical content, so I'm going to immediately disappoint you by talking about policy. Yeah, I'm Paul. I'm now working for the Yocto project, and I'm going to talk to you today about Yocto project and the Cyber Resilience Act. Who am I? Yeah, as I say, I work full-time for the Yocto project now. And I essentially act as a leverage function for our project, so help to coordinate our activities, help project to scale effectively, and do still manage to get my hands dirty with a bit of implementation and debugging, which is very nice. Contents for today. I'm going to give an introduction to the Cyber Resilience Act. What is it? Why should you care? I'm going to talk to you about the context specifically of the Yocto project, where we are today, what existing features we provide to help with CRA compliance, and I'm going to talk to you about Yocto project tomorrow. So how can we meet our new obligations and how can we help you meet yours? So let's start off with an introduction to the CRA. So the important slide, this is a high-level introduction only. I'm not a lawyer. This is not legal advice. I am just one person within the Yocto project, so I say we quite a few times in the slide. But do bear in mind, projects are made up of multiple people and views may differ between people. Obviously, consult your own legal advice if you have any questions. So what is the CRA? I think, quite a few people here will be familiar with this already, but probably not everyone. So the Cyber Resilience Act is a piece of EU legislation. It has already been passed. It's already law within the EU. It regulates cybersecurity. It regulates availability of vulnerability fixes, support period, and these things for what they call products with digital elements. And a product with digital element, essentially it's any product that has some sort of network or data connection. So that is going to encompass a lot of the things that people in this room work on. It is important to say that there are specific industries that people work in that are excluded because they're already covered by existing legislation, so automotive and medical. In those industries, people will already be used to kind of compliance processes. For a lot of us, this is new territory, though. The main thing to start off with is the categories of different actors under the Cyber Resilience Act. So the legislation considers two types of economic actors. It considers manufacturers, that is, companies or individuals who build products. And it considers this new type of thing that they've essentially had to invent out of whole cloth, because it didn't exist as a concept before, of an open source steward. And everyone else who isn't a manufacturer, isn't an open source steward, out of context, out of scope of the CRA, don't need to worry about it. It's also worth highlighting that the designation of whether you are a manufacturer or an open source steward is per product or project. So a single organization can be the manufacturer of a product that they sell and the steward of an open source project they run. So what is a manufacturer according to the CRA? So this is any organization that is placing a product on the EU market. And this includes many free products and services. So if a company provides a product for free, but in exchange for that they collect data from the users, then that's still placing a product on the market. And for manufacturers, the full regulations apply. And it gives some highlights. This is not a comprehensive list. But manufacturers should be avoiding known exploitable vulnerabilities. They should be tracking the software components in their product and the vulnerabilities that apply to them. They should be reporting incidents and vulnerabilities to relevant CSERTs. They should be providing security updates for the useful lifetime of the product, and that's the key one really, is that need to provide security updates. And in many ways, this is essentially taking consumer legislation that applies to other products and saying, you also have to think about this if you're doing software. So other requirements, manufacturers need to do a cybersecurity risk assessment, and this is going to be the starting point for most manufacturers. This is the thing that's going to inform what actions and mitigations they need to take in relation to the risks that they've identified. And also need to create technical documents and software bills of materials. These don't need to be published, I don't think, but they must be provided to relevant authorities on request. For specific classes of product, there are a higher level of additional requirements and standards that may be useful to follow, and there may be a need to get third-party certification. This covers things like operating systems, routers, firewalls, password managers, browsers, things where an exploit in this particular piece of software or product could have strongly negative impacts on people. So that's the manufacturer side. The other side I want to talk about is this idea of open source stewards. And this is something that they've identified as almost a middle ground, really. So organizations that are responsible for maintaining a piece of free and open source software that is intended for commercial use, or you can reasonably expect will be used in commercial products, are designated as open source stewards. And they're subject to this kind of light touch regulation. So the requirements on them are essentially you must have a compliant cybersecurity policy, and you must cooperate with the relevant authorities if they ask for information to help them in an investigation to do with a manufacturer's product. And the important thing for people who run open source projects in the room is there are no fines for non-compliance. They expect people to follow these regulations. They will, probably give people a nudge if they're not doing, but they have said that they do not intend to fine open source projects for non-compliance, which is very good news. So the criteria, there's been, people have been trying to figure this stuff out, and the conclusion that people have come to when people like OpenSSF and others have looked at this is you don't really decide whether you are an open source steward or not. There's a set of criteria, and if you answer yes to all of the criteria, congratulations, you're an open source steward. So Is the organization a legal entity? So that is a company or a non-profit organization, specifically not an individual. No single person in this room will be considered an open source steward. You might be employed by or be contracted by an organization that is an open source steward, but you as an individual are not an open source steward. Then, is the organization responsible for publishing the free and open source software? If not, not a steward. Is the organization providing what they call systematic support for the free and open source software? So that's things like employing maintainers, hosting development services, that kind of ongoing support for that project. And is the software intended for commercial use or reasonably expected that it will be used commercially? So these are criteria. There is some draft guidance which has included a lovely little flowchart. I recommend finding this in the slides because I don't know how well this is visible here, but yeah, there's essentially, they've given us a nice little flowchart, and this is from the EU, so straight from the horse's mouth, that kind of tells you where you might fit in. So I recommend if you are unsure, go have a look at that, work through it, see where you end up. It's also worth emphasizing here what is not in scope of the Cyber Resilience Act. So individual contributors or companies that contribute to an open source project, the CRA doesn't tell you to do anything. You are out of scope. And very obviously, non-commercial open source projects. So if you maintain some small project that scratches your own itch, the CRA doesn't affect you. So this is specifically going to be for large open source projects, things that are heavily used within the commercial space. I do want to give a shout out here to the Open Source Security Foundation because they're doing excellent work in the area of just trying to parse what this thing is and what we need to do about it. They've published some great resources, they've got mailing lists, they've got calls that people can get involved in. So yeah, I think they're the people to go and work with for more information there. So I'm just going to grab my water. So let's talk about the Octo project, which is what I work on. I am making the assumption that most people in this room do know what the Octo project is, though you don't need to know specific technical details in order to understand this. What I want this to be is information about what we're doing, how we see things, but also hopefully a bit of a case study, so you can use this to inform how you think about the projects that you're working on. So, first question really is the Octo project in scope of the CRA? Well, the Octo project as a thing is a legal entity, technically under Linux Foundation projects. So TIC, we are a legal entity, we're not an individual. We do publish open source software. That organization, the Octo project, does contract maintainers. It provides repository hosting, and we run the Auto Builder cluster, which is our CI system for the project. So TIC provides the ongoing systematic support for the open source project. And the Octo project is clearly intended for commercial use. It would be very difficult to argue that it isn't, especially with the presence of commercial memberships through the Linux Foundation for the project. So essentially, we do tick all that criteria that says, yep, we are in scope of the CRA. So the next question comes, well, are we a manufacturer or are we an open source steward? And this is essentially, is the project that we work on a product with digital elements or not? And we've looked at this, and the conclusion that we've kind of come to is we think we are a steward. We don't charge for access to the software. We don't collect user data in exchange for using the software. The commercial members of the project have influence, but we don't give them dedicated support in exchange for that membership. We don't give them specific consulting for their use case. So that's not really selling a product. And, you know, we're a non-profit organization. So this, on that little flow chart I had earlier, ends up with us landing clearly in the bucket that says open source steward. And I'm going to come back to my earlier caveat slide. I am using the word we. I am talking about the Yocto project. But this is, you know, the conversations that a few of us have had and our attempts to work through this and figure it out. It's a best effort. And really, until we get further down the line and there is, you know, court cases and other things down the line, it's not going to be 100% clear where all the boundaries are. But this is what we think today, and this is, you know, how we're going to approach things. So, given that, how do we see the CRA? What do we think about this? To the Yocto project, the CRA is a challenge. We will need to adapt. We will need to put a couple of new things in place. And our users, particularly the people who are manufacturers of products with digital elements, will have their own obligations they need to meet, and they will be coming to us with kind of higher expectations and things that they want. But I would also say that this is an opportunity for a project that tries to provide best-in-class tooling that already has a very strong and quite well-informed community of companies who are building and manufacturing products and thinking about compliance in various ways. I think we're quite well placed. And the build process that we have makes it quite easy to collect sort of required metadata and provide the sort of options that people want. So I'm going to run through some of the sort of tooling and things that are provided by the Yocto project and how that fits into meeting people's needs with the CRA. I'm not used to this warm weather. So yeah, tooling. Yocto project is essentially tooling. And one of the things we provide is software integrity. So if you want to ship something and be confident as to what is in this, so that you can provide an accurate software bill of materials, and that you're actually shipping the software that you think you are and not some maliciously replaced source tarball, it's pretty important in terms of being able to comply with rules around cybersecurity. So we already have tooling to cover this today. So the way that Yocto project goes and fetches sources, it validates cryptographic checksums, git commit hashes during the source download. We also provide binary reproducibility, which makes it easier to verify that the thing you've built is the thing you intended to build. We do have options to sign the shared state that is used for caching build data and generating signed package feeds. And the new layer setup tool, which is Bitbake Setup, can also verify the git commit hashes of the various metadata layers that you might use in a Yocto project build. So this collected together allows you to have some level of confidence about the integrity of the software that you are building. We also have a plethora of options for over-the-air update. There is not a single over-the-air update solution within the Open Embedded core layer, but what we have is this ecosystem of both open source, non-commercial, and commercial solutions to these problems. And via these third-party layers, we have support for various different over-the-air update methods. So SW Update, Rauk, and there's also commercial vendors in this space like Mender. So lots of different options here, but most of these have very good integration with Yocto project. So this allows you to meet that requirement for providing security fixes for the reasonable lifetime of your product. We also have tooling to generate software bills of materials and to track CVEs. So we now generate SBOM documents. The new LTS release that's just come out defaults to SPDX3 format, which should be standardized fairly soon, I believe. We support package URLs or PURLs, which are the new shiny thing. So this is essentially a way of uniquely identifying a particular upstream software package and version. And we've recently integrated the SBOM CVE check tool that was developed by Bootlin. We used to have this thing called CVE check class that you could enable during a build, and it would give you a report at the end of the build of what vulnerabilities exist in this software image that haven't been patched. And that was useful. But SBOM CVE check, it does that analysis based on the SBOM that has been generated during the build. And the thing there is that SBOM is a file that comes out of the build. So you can take that SBOM and you can rerun SBOM CVE check 3 months, 6 months later, and answer the question, what new vulnerabilities have been discovered since I built this image 6 months ago that I need to go and triage and respond to. So this is a really big improvement over what we already had. We also have source mirroring and archival tooling. And this doesn't really sound like this is relevant to the CRA, but I would argue that it is. Upstream sources do disappear off the internet. If you're shipping something that's using various open source components, and you want to come back a year later and just change 5 lines to fix one security bug, sometimes you do find that the source code for that has disappeared off the internet because somebody got bored and doesn't want to maintain it anymore, or company went out of business or something. So having your own copy of upstream sources is the thing that ensures you can go and investigate issues, you can go and patch things later on. And further to that, I would say one of the key things that we provide is autonomy for people who want to build and ship products with embedded Linux. And this isn't just a Yocto project thing, this also applies to Buildroot and any other type of embedded Linux build system. What this allows is you to take ownership and ensure yourself that your obligations are met. So there is no single software supplier here to act as a bottleneck. There's nobody you need to go and ask for permission if you want to fix a particular issue in your software image that you're shipping. There is no enforced services that you have to connect to. There is no enforced data collection, which might then, include its own security vulnerabilities that you then have to deal with. You choose what goes into your software image or what doesn't. And I think this is, these are things that we are all familiar with. These are the benefits of open source. But I think in the context of CRA, this autonomy really is a feature. And another thing that's really a feature is you're part of a community. We've got a CRA working group within the Yocto project, which meets bi-weekly via a Zoom call, and please join us. This is a good venue for discussing concerns, learning from other engineers in the community, and sharing what you've learned. And where groups like OpenSSF take the kind of wider view around security and compliance, with this working group within the Yocto project is a bit more narrowly focused on the organizations that are using Yocto projects and shipping embedded Linux products. There are some limitations here. There are some things the Yocto project can do, and there are some things the Yocto project cannot do. And again, we're not alone in this. This is going to be the same with any other build system you use. We can act as a responsible open source steward for our project. We can provide tooling and collect best practices to help the users within our community that are manufacturers of products. What we cannot do is give you specific instructions for how to comply with your particular products. And what we especially can't do is meet your obligations for you. So all this is wonderful, and I think we are really well placed within the Yocto project, but if you're working for an organization that is shipping a product that falls under the CRA, you need to take ownership of this and make sure that those obligations are met. Next, I'm going to talk about where do we go next with the Yocto project in relation to the CRA. So I did say we have some new obligations that we will need to comply with. The main thing we need to actually go and change is we need a cybersecurity policy that is compliant with what the CRA says an open source steward has to provide. And essentially there's a list of things that we need to do. This policy needs to encourage secure product development, encourage effective vulnerability handling, encourage voluntary reporting of vulnerabilities. It must address how we document and remediate vulnerabilities. This doesn't necessarily mean we need lots of paperwork for every CVE that we find, but we do need to write down and make sure we're communicating clearly what is our process. We have to promote the sharing of information, and we should document how we plan to handle the other responsibilities that we have, which is the reporting and the cooperation with what they call market surveillance authorities. This is essentially just the relevant regulators within different EU countries. And we have some of this documentation already. We have a security manual within our documentation. This is essentially just adding a little more to it and making sure it ticks the specific boxes that the CRA is asking for. We have reporting requirements, so we have to notify these authorities if we find actively exploited vulnerabilities that we are aware of. This is not, we don't have to start reporting all CVEs that we know about. This is if we become aware that something is being actively exploited and we know it hasn't already been reported. We have to notify about severe cybersecurity incidents that may impact the security of downstream products. So this would be something like if we found that someone was able to do an unauthorized Git push to one of our repositories. We have lots of security in place that means that should never happen. If it did, we would have to notify relevant authorities. And we have to inform impacted users, preferably in a structured machine-readable format. In practice, this will be via posting to our mailing list. There are a couple of other bits and pieces. We need to define the project scope clearly for the CRA, so what is in context for that, in scope of that security policy and what isn't. We have to collect some evidence, so if we do end up reporting something, we just want to collect that that is a thing that we've done, so that if we're asked, we can say, we can prove that we follow our own processes. And we should be moving our security documentation, some of which is in our wiki, into the proper version control documentation. We do want to then, those two slides are kind of the things we have to do, then we move on to things we would like to do to improve things. We are pursuing funding for work in development of a threat model. We are also hoping to audit the integrity features provided by the Bitbake fetchers and audit the various network accessible services that we provide that people can run. That includes things like our layer index, error reporting service, hash equivalence server, PR server, these things. So hopefully we'll have further updates on that soon. Two areas where I would like to see improvement within the Yocto project, and this is things we should do, things I would like to do. One of the things in there in the CRA is explicit guidance that products should not have kind of a static login credential that's reused across all products that you ship. So you should not have, admin123 as the login credential for a router, because then when you sell 100,000 of them that are connected to the internet, that one credential can be used to build a botnet. There's multiple options available to address this. We should integrate one or more of these. So you could provision device-specific login credentials, perhaps derived from something like a serial number or unique product ID that can be printed on a label or put on a card in a box or sent by email to someone. You can also prompt for creation of username and password during initial setup. We could also integrate tooling that exists to handle this within desktop Linux distros, so Cloud Init, Ignition, other projects like this. We should also integrate secure boot support. I would argue that secure boot is very, very hardware specific. I would argue that to do secure boot properly requires that that is a requirement from day one, and that you do secure hardware and software co-design from the early stages of product development. You can't just, tick the I've enabled UEFI secure boot and therefore I have secure boot. You need to actually think about this from a, PCB components, connections, what the chips you have do standpoint. But what we should be able to do is provide a reference implementation in our emulated machines, typoed QEMU, and board support package vendors should be encouraged to provide hardware-specific reference implementations of how to do secure boot for their SoCs and boards, and I think some already do. Ideally, we would have at least one reference platform for the Yocto project, which has fully integrated secure boot support. We should be able to migrate some of the common secure boot features into our core metadata layer. And then we should be able to test this in an automated way using QEMU. So UEFI secure boot, we can do kernel signing as part of the build. We should be able to dynamically generate keys, do the signing, load them into UEFI, on QEMU and actually verify that this thing boots securely in QEMU. We should be able to integrate Opti into our core layers now because it's used by 2 different architectures, RISC-V as well as ARM. And we should be able to enable the TPM2 emulation in QEMU and use that to validate the user space TPM tools. And although this emulation stuff is a bit different than secure boot in a physical product, it's really important to have a reference to validate these different interfaces and to help show people how do you do this. Then we have possible improvements to the SBOM and CV tracking. So we support SPDX3 as a data format. The other competing standard in this space, as we all know, the best thing about standards is there's so many to choose from, is Cyclone DX. So you could add support for that. There's also vulnerability exchange format, VEX. Have support as that as an input format, but we should also be able to use it as an output format. We want to add support for additional data sources, so we don't want to just rely on the US NVD as a single source of CV data. There is EU vulnerability database, there are other data sources. OpenSSF has a malicious software list, so this is things like typo squatted versions of projects that have malicious code in there. We should be able to pull from those data sources and track against those. And we should work with these data sources. We have various assignments for this CV status variable within our metadata that tracks additional information that we know about particular vulnerabilities. We should try to get that data upstream where we can. Also SLSA attestation, also retirement of obsolete recipes. I'm going to skip forward a little bit so there's some time for questions. 2 things here. One is, should we become, I think this is open operating system vendor. This is about providing particular data about CVEs. This is a maybe. We could have our own feed of CV information provided by the Octo project. This would allow us to easily exclude things that are not applicable when you build with the Octo project. But the con is it would require significant long-term resource investment because we would essentially have to pass through every single upstream CVE by re-reporting it in our own data repository. So that's a maybe. Should we become a CVE numbering authority? That is a categoric no. It's not worth the cost for the Octo project. It would only ever apply for software that we directly publish, so BitBake, metadata, some of the components we provide. And the scope there is quite narrow. The overwhelming majority of CVEs we deal with are in upstream software that we have recipes for, not in direct components that we could be a CNA for. The important thing here is contributions are needed. So the question, what security and compliance features will the Octo project have? That is determined by what contributors choose to work on. This is an open source project. We have some limited amount of resources within the core team to go and implement things ourselves, but that is limited. We are pursuing funding opportunities. Even if those are successful, that's not going to cover everything that we would like to achieve here. So, this is a shout out to please help join us to continue improving the Octo project. Then I have some resources and appendices which are here. I recommend going downloading the slides. There are some links here, including CRA, draft guidance, OpenSSF resources, more resources. If there are any questions, this is copy-paste from the relevant bits of the CRA about stewards. Thank you. Questions?
How does it work? Okay. Thank you, Paul. I have a question concerning the CVEs tracking and fixing. Is best effort from Yocto to fix them, or at least for the LTS branches?
So in terms of how are the CVEs fixed on the LTS branches?
Yes.
So there are various people within our community who have to fix the CVEs in their
Have,
products,
okay.
and a lot of them, rather than having the burden of having to maintain their own fork, they find it easier and better to contribute those CVE fixes back. That's where most of the CVE fixes come from. We also have an LTS maintainer who looks after the LTS branches. That person is one person. They cannot fix every single thing themselves.
So,
But
so
I think
it's
we do a
just
pretty good
best
job.
efforts, not to have like a user of Yocto expecting that every CVE will get fixed.
It's an open source project.
Okay,
We don't give written guarantees.
okay. Thank you.
So you mentioned that the EU said they're not going to look to fine open source stewards. Have they given any indication what their process of nudging would be someone who didn't comply?
Not that I know of. The one thing I didn't kind of put in here was the timeline. So the CRA has passed legislation. It is in force. The vulnerability reporting requirements come in later this year, and then the full regulation end of 2027. So some of this, how is it going to be enforced and implemented, is still being figured out.
We'll wait for the court cases, I guess.
So about the CVEs, you said CVEs or security vulnerabilities from Bitbag and stuff like that is responsibility for Yocto. The upstream packages are responsible for their issues, but Yocto, or basically any embedded build system, they usually include patches as well to the upstream patch. What happens if a patch introduces a security vulnerability? Who is responsible there?
So I would address that in a slightly different way, which is we have a very strong policy that patches should be submitted upstream. We carry some number of patches. I think we have around 1,000 patches in the core metadata layer at the minute. But of those, I think there are 150, last I checked, that were in this kind of pending, we haven't submitted them. So the actual number of patches that Yocto project is carrying that aren't backports from upstream is quite small. So yes, if one of those introduced a vulnerability, that would need to be fixed in Yocto project, but that is quite a small surface area compared to the amount of upstream source code.
Yeah, of course, fixing is clear, but is there any requirements with respect to reporting and these kind of things?
The requirement for reporting is around actively exploited vulnerabilities. So if someone within our community sent our security list an email that says, oh dear, all of our projects are being exploited in the wild, and they haven't gone and reported it to you, that's when we would have an obligation. But there is no obligation to fix every CVE, especially not on open source projects. There is one more here. I think where are we on time? One more.
The collaboration with MSAs, do you have any ideas about that already?
So, as earlier, I think some of this is still being worked out. In terms of how it is structured, this is why I've put these slides in here. It's in the context of a view to mitigating cybersecurity risks posed by products that manufacturers make that use that. So it's, quite caveated. I don't think this is going to be kind of tons and tons of ongoing work. But that's where we are at the minute in terms of our knowledge. We'll have to figure it out. Some of this stuff we're not going to know. It's like, in some ways, it's like the GDPR. It took years after it coming into force before people even started to understand it fully.
Okay, you told that CRA mentions multiple types of classes of products, and one of the classes is routers. But I understand that this is the regular IT router, not any router from random protocol A to random protocol B.
I mean, the question of what is and isn't in all those product categories is outside the scope of what I'm thinking of in terms of the Octo project, so I wouldn't want to try and make a guess on that. I'm not
Okay.
the right person to ask that.
Okay, thank you.
Cool, thank you very much.
Why doesn't it show?
Stop again. I have to switch to the mirror.
I think I did.
There.
Yeah. It's currently mirror. You want to
Yeah.
try the other adapter? Oh. And we couldn't join the.
You could try it. It worked.
I think the password was wrong.
Oh, it's this event.
If you don't manage now, I can join with my. I'll just open the 5G on my
Okay.
because I need.
You need the Wi-Fi?
Yeah, I need Wi-Fi to start the slideshow. But why doesn't it show up in there? I don't know.
I think I had to switch it to extended instead of to mirroring, and then I had to drag the screen.
To get over the Wi-Fi issue. Yeah, it's okay. Did you switch it?
No. Okay, so now if you go here,
Choose content.
there we go. Choose. There we go. Do the window. See if you can do the window, or no, extended. I think that's what. There it is. Yeah. It shows it here, and then switch that. Yeah, that's the right one. That should work. That's right. That's right. Okay, now go to the other. Go to your.
It said mirror obligations.
This happened yesterday.
It's always there. Yeah, choose that. Do you want to switch? Try this one.
We can try that one. Yeah.
The reason I brought mine is that it actually worked. Yeah, start the slideshow. There's one, thanks. I mean, this is, yeah, this is good.
I'll have a flashlight in the front row when it starts getting time. We want to switch to questions.
Yeah, I'll be fine. I think I'll be fine. All right. Hello, everyone. I'm Elias. I work for Linaro. I currently serve as the custodian for U-boot CFI subsystem, amongst other subsystems. And there's been a substantial amount of work done in U-boot the past 6-7 years regarding EFI and booting. I don't think that has been discussed previously widely on an audience, so this is the perfect place to do that. This is quite a big topic. We're going to start with the basics on EFI, right? Go through the variable services, secure boot, everything you need to enable on your board. Look how you enable measured boot, which Paul mentioned in the previous talk as well. How do you do capsule updates, which is EFI's parlance for firmware updates, and eventually how to get to a point where you can boot an off-the-shelf distro or Yocto or any distro you want, either via HTTP or directly, or run an installer and finish up the installation. So, UEFI. UEFI is an extensible firmware interface, right? It was originally proposed by Intel. It's a modern replacement for the old BIOS. It's basically there to start your computer and get out of the way as fast as possible. One common misconception and things that we've been discussing over and over again is that EFI is not an implementation, right? UEFI is a specification. It defines the interfaces of how you do that. We have various open source implementations of an EFI firmware. One of them is EDK2. U-boot is another implementation which has reduced scope compared to the EDK2. And then you also have your commercial implementations that exist. As I said, its main purpose is to give you an abstracted way to boot and load your OS, right? That's the goal. It has some security primitives baked in, and it's also extensible. So for example, the secure boot is part of the EFI spec. Measured boot is not. It's an extension to the UEFI spec, which is described in the TCG documentation. It also has protocols to do file authentication, authenticate binaries, extra binaries you need, etc. It also describes how firmware updates should be treated. An important description and a building block of UEFI is the services, right? The distinction there is that EFI has boot services and it has runtime services. The boot services exist to boot your OS, boot the image you want, and start your existing OS, and then you move to the runtime services, which survive and exist while your operating system is running. The easiest way you can think of it, and the easiest way I could think of it when I started was protocols are basically function pointer callbacks that you can discover through a GUID. This is a unified view of the EFI world, so you have your boot services, your runtime services, and your protocols. Protocols is what you use to basically implement all the services you want. You have timers, memory allocation, booting OSs, all that stuff. What mostly survives at runtime is the variable services, time services, and some memory services. You also have configuration tables, which is a way of EFI to communicate to the OS various configuration like your ACPI, your SMBIOS, your device tree, et cetera, et cetera. So, for embedded boards, the UEFI spec is too big, right? The spec itself is enormous. You don't need all of it. So there was an effort started a couple of years ago, which is called DBBR. That's the embedded base board requirements. It's trying to do the same thing, right? They define an interface between your firmware and your OS that they can interact and load in an abstracted way. It's basically a subset of the EFI spec with a very reduced scope and some very small deviations from it. ARM also went a step ahead, so they have a compliance program that you can run and test the device for interoperability. It's a collection of standards, so you have the BSA, you have EBBR, you have the device tree spec, but the important thing here is that they provide a test suite you can run on your board and make sure it's compliant. So how this whole thing started. U-boot got UEFI support back in 2016. It was rudimentary. We could prove, we convinced that it works, and we convinced that it can boot multiple distros. We had to do a lot of manual queries back then to actually boot them. And 2021 was the first actual release that U-Boot passed all the certifications and all the tests and everything on the system ready that ARM provided back then. We still needed small quirks here and there on distros and the installers, but they were way smaller than what we needed in 2016, and we could boot a lot more distros than we booted back then. So along the course of time, we added variable support, which is essential for booting and maintaining your distro, secure boot, measured boot, authenticated capsule updates, HTTP support, so you can run a distro and boot EFI images over HTTP, RNG support, which is kind of a requirement for kernel's KSLR, a small part of it anyway, and we added the UEFI boot manager, which is a part of the EFI specs that, think of it as Grub, right? You can define boot options and methods and device trees and everything you need to boot your OS without Grub. Distros still rely on Grub on systemd, but that's an implementation detail. We also added generic features. So when you boot U-Boot, you now get access to 2 tools to configure the entire flow of EFI. You have EFI config, which is an interactive configuration tool. And we have EFI debug, which is the equivalent, but it's a command line tool and it offers some debug functionality on top. What the UEFI spec doesn't mandate, but it's really good to have, especially if you're looking in doing products, is dual banked firmware updates. So when you update your firmware, how do you go back? How do you not go back? How do you maintain that? How do you maintain your rollback counters, etc.? So there is a specification that describes how to do that. We'll talk about that later in the presentation, but U-Boot does have support for that as well through the EFI capsules. So the variable services is the first topic that we had to tackle. Those are used mainly for secure boot, boot management, and some OS to firmware communication. It's important that and it's funny that the EFI spec doesn't describe any of that, right? It doesn't describe where to store the variables, how to store them. It doesn't describe the format. The only thing that it says is that they have to be protected. The initial U-Boot implementation we had back in 2016 was storing the EFI variables as traditional U-Boot environmental variables, and that was fine. That was the easiest way we could do, and it made sense back then, right? Turns out that when we tried to implement authenticated variables, things weren't so easy as we imagined. So we ended up splitting them. U-Boot has the traditional environmental variables, but the EFI subsystem has its own view and its own storage for variables, which you can, if you add the -e flag on your usual commands, you can see the EFI stuff part. It's also important that U-Boot has, as you have the environmental variables and you have multiple backends for that, U-Boot also has multiple backends for EFI variables. The difference is that the backend you choose actually has an impact on the security that you have and how easy it is to use them on the board. So you basically have 3 options. One of them is we store the EFI variables in a file in the EFI system partition. That works great for devices that don't have an alternative, right? If you have a device that just has an SD card, that's great. It works great. It gets a bit clunky once you have more than one ESPs because U-Boot doesn't have a way to define which ESP to use for the variables. So if you start plugging and unplugging USB devices, you randomly see variables disappear depending on when you wrote them or why you wrote them. And it's the easiest solution we have, and it's fine as long as you have a single ESP. Set variable at runtime, which is part of the EFI services, and allows you to change variable at runtimes. This is what allows you to change the boot order on your computer, etc. Back when we started thinking about eBBR, I think we never understood how important set variable at runtime was. So it's important that we get to the point where this is supported now. On the other hand, authenticated variables which control your EFI secure boot are not allowed. You can't store them or change them in that configuration, and that's deliberate. I mean, if you store your security critical variables on a file and someone just deletes the file, then he can just boot the board. But you can still implement UEFI secure boot, and we'll get to that once we discuss the secure boot part. You can also store variables on an RPMB. Now, this is interesting. It requires a few more firmware components. It's not easy to implement, and it's not easy to plug on your board, but that solution works with multiple ESPs. The reason it works with multiple ESPs is that you have a single source of truth, right? You don't have multiple places where you can store the variables. They're only stored on your RPMB partition. Set variable at runtime does work, but it only works on the kernel. It doesn't work on other operating systems, and there's a reason that we'll, again, discuss on the following slides. Authenticated variables, though, are properly supported. So you can have a full UEFI secure boot implementation where you can read, write, and update your variables at runtime. And this is actually a great solution if you have an embedded board that has only an eMMC and you want to implement all the security features that exist, or add the boot with EFI, have the UEFI secure boot enabled, and also have TPM support for measured boot. As I said, this is pretty complex. If anyone is interested on the presentation, there's a link to a blog post that describes exactly the engineering behind how this was implemented and the reasoning why it was implemented like that. And finally, you have UEFI variables on a SPI flash. This makes sense. I mean, most boards have a SPI flash. We can store the environmental variables. It follows the same rule set, right? You basically store them in SPI blocks. Set variable at runtime is not supported yet. But it works with multiple ESPs, right? There's, again, as with the RPMB solution, it doesn't matter if you have a single storage for the EFI variables. It doesn't really matter. The number of ESPs becomes irrelevant. This is very similar to the file storage in the way we treat the secure boot variables. So they're bound by the same limitation as file storage. You can still enable UEFI secure boot with a small caveat on it. So UEFI secure boot, that's another controversial topic. So one very significant point is that UEFI secure boot is not there to authenticate all of the files you want to run, right? So you can't authenticate your init from FS, your device tree. Those have to be authenticated differently. The only thing that UEFI secure boot does is authenticate the next UEFI binary you load. It makes sure that it's signed by a private key that exists in your public key chain. It launches that application, and then it's up to the application to delegate the security to the next component. So what we usually do, for example, in Linux, we have SIM. We first load SIM, that then loads grub, and eventually loads the Linux kernel. But the authentication of the Linux kernel is not the responsibility of the firmware anymore. It's the responsibility of grub or SIM or whoever is next on the chain, last on the chain. It's basically controlled by 4 variables. You have your platform key, which is the master key for all the variables that follow. You have your key exchange key, which signs the security database and the excluded database. And then you have your databases, which actually control the execution of the binaries you're allowed or you're not allowed to run. It's pretty obvious that the security basically depends on how secure your storage is. I mean, imagine that you store the variables on a SPI flash and someone just unsolders it and solders a new one with legal certificates. No one will figure out that anything went wrong, and then he can suddenly boot his own binaries that are signed by his own keys. That's the reason the UEFI spec is strict about them and tries to prevent more attacks. So it requires them to be stored in a secure tamper-protected storage. And that's irrelevant, but for size reasons, we don't always enable secure boot. When we enable EFI and U-boot, you have to enable it manually. It's a config option. So variables in a SPI flash. So as we discussed, as I said, this is completely unsecure, right? We store them on a file. The file can be deleted, corrupted, moved, changed, and no one will will understand that this ever happened. So for that reason, you're not allowed to store, modify or load authenticated variables from a file or a SPI. Basically, that's a common pattern that we intend to keep in U-Boot, right? Whenever we load variables from an authenticated way or from a storage that we don't trust, we won't allow authenticated variables. What U-Boot does allow you, though, is to build all the EFI keys, all the entire EFI keyring in the U-Boot binary, and it sticks it in a read-only memory area. So if you have a proper product, like was discussed before, and someone authenticates your U-Boot prior to loading it, then you basically extend the chain of trust, and you trust the secure boot keys. And you can boot your binary with UEFI secure boot enabled. The obvious caveat is that if you want to update any of the authenticated related security variables, you have to update the entire U-Boot, right? It's part of the binary, you can't do otherwise. You can't change the binary, or you can't change part of the binary because it's signed and authenticated by a previous stage loader. So that's the downside of having the variables on the SPI. Now, variables in the RPMB. This is a proper implementation. You can update them on a running system. You can do whatever you want. It behaves like a normal system. You have complete control over the variables. Opti is responsible in that case for the RPMB key and the EFI variables, and that never the processing or the keys or anything we do never leaves the secure world of ARM, at least for ARM. It reuses standalone MM, right? So when we did the entire development, we figured out that instead of rewriting everything, it would be easier and better for everyone to run an application that we know and trust and has been debugged and tested over the years, rather than doing it over from scratch, right? So instead of writing from the beginning, we figured out that we could launch standalone MM from EDK2, completely sandbox and isolated in Opti. It's even isolated from the rest of the Opti trusted applications. And it's the same application that we use on servers, right? The difference is that on servers, we don't usually traditionally care for a secure world operating system, so we just load it as a bare metal application on secure world. On embedded, because we want extra functionality, we prefer doing it via Opti. I'm not going to explain that, right? This wasn't the purpose, this was the purpose for you to look at it. But this is basically the architecture of how U-Boot calls Opti, Opti jumps into standalone MM, comes back, and we're using Opti APIs to basically write and read and write the RPMB storage. That was the purpose. Measured boot. So it requires a TPM, Trusted Platform Module. It can either be a hardware TPM or a firmware TPM. We don't make a distinction, mostly because the TPM is described by a spec. So as long as your device is compliant, we don't really care where it came from. There's also a software implementation for a TPM, which is really nice because we can test everything on QEMU. Measured boot is completely different, right? Its job is to measure various components of the boot order. Your ACPI tables, your SMBIOS. There's a spec describing basically everything that you have to measure, and you can extend it and measure more. But it basically measures the entire sequence in platform configuration registers. U-Boot implements the PC client specification, which is part of the TCG specs, and it's what made sense for embedded boards. It's controlled by these parameters, and the reason this is important is that we're measuring the device tree as well, which goes over and beyond the spec, right? The TCG specs, unfortunately, don't have a way to describe how to measure the device tree. What we actually did is basically copy what they do for ACPI tables and measure it the way ACPI tables are measured. This is enabled by default, and it's automatically detected whenever you boot a board and a TPM is there. So you should see something like that along the way, right? You should see a TPM final event log on your D message or an event log, and you can even read the events from Linux's user space. Again, really important, measured boot doesn't prevent anything, right? Measured boot is there to tell you that, hey, someone changed something along your boot chain and notify you. It's up to the OS vendor, the implementer, everything to do either local or remote attestation local sealing or remote attestation or whatever the security policy they chose is, but it won't prevent you from executing a binary that's not supposed to be executed. But it will measure it. Capsule updates. So that's EFI parlance for updating your firmware. The spec defines two ways to do that. You have runtime capsules and you have the on-disk variant. U-Boot implements the on-disk only. That was a policy for various reasons. But the short version is that the spec defines a folder which is standardized. You copy the capsule there. You set a variable that basically tells the firmware, I have a capsule for you there that you can fetch and update, and then reboot. As I said, we have the CFI debug tool that is used for debugging and various other activities. So you can run it on the command line, but the proper way to run it is through the update mechanism, the reboot mechanism. U-Boot provides a tool to create capsules, and the authentication is not mandated by the spec, right? The spec describes it. It doesn't say it has to be authenticated. LVFS and FWD already support on-disk updates. So if you, we'll get to it on following slides, but if you package it properly and upload it, you can update the firmware through LVFS today. So not all boards have support for that. You don't have support for all of the boards. That makes sense because that's a board-specific thing, where your firmware is stored, how do you update it, how do you write the flashes. And it used to be pretty complex on how to add. Everyone was doing something of their own. Now, luckily, we've standardized this over the years. So you basically have to define the number of images you want to update, the DFU command you want to use, the device firmware update command you want to use, because in the background, that's what capsule update mechanism is using. And a GUID that's unique per image. And that's not even needed nowadays because we had people copy-pasting the same GUID when sending patches. So we have a mechanism of basically creating as many GUIDs as we need per board in a reproducible way. This is basically what you have to add, right? That's all you need to enable a capsule on your board. It might get weirder or more complex if you have more indexes or more images, if your firmware comprises from more images, but that's basically all you need. This is not mandated by the EFI spec. It's really good to have. It's not, the design is not too fancy, right? It's based on capsule updates. Unfortunately, it's not supported on U-Boot's SPL. It's only supported on trusted firmware for now. Basically, when we do an update, we switch the board on a trial state and we boot to an OS. The OS can run a number of tests, which are implementation defined. We're not going to tell you what to run. But as long as you're sure that your new firmware, which interacts with the OS, whether we like it or not, works, then you can ratify the update and say, okay, you can move on now and mark this firmware as accepted. If at any point in time a configurable number of reboots happen, we just switch to the previous known working firmware. This is basically the flow, right? That's the basic idea behind. It's not, I mean, it's the basics. That's how you should update your boards. And another important functionality over here is that the image acceptance happens through a capsule, right? You update your firmware, you go to the OS, you install a special capsule with a special GUID that basically tells the firmware to accept the firmware permanently, but you can override that, right? And that's what the image on the top is trying to show. The moment you create your capsule, you have the option to say, I want to delegate this possibility of accepting the firmware to the OS because I want to test it. Or you can create your capsule and flip that config option and say, I know what I'm doing. I'm pretty sure my device is not going to break. I just want to accept the firmware immediately, and I don't want you to wait for the OS to test it. And that's not part of the firmware, right? The important part is that this is part of the capsule creation. You control it when creating the capsule, so you don't have to update to switch between functionality. So LVFS is integrated, as I told you. We've worked with Richard, and he was really helpful. It's the Linux vendor firmware service. It's basically part of every distro. You can package and upload your firmware to the website, and then with just a single command, update your firmware. You even get notified if there's a new release. HTTP. So having the ability to run distros is helpful, right? Nowadays, from U-boot, you can boot live images as long as your board has enough DRAM. We started off by adding wget support, but then we figured out that the existing functionality in the TCP stack were, first of all, limited, and second, adding HTTPS in the long run was going to be too difficult, right? And on top of that, the user had to do that to run. I mean, you had to execute 5 different commands just to boot, map, load, and run a distro. So we decided to change that. We decided to this was a fundamental decision for U-boot, right? We decided to use external libraries for the first time. We worked with Embed TLS to change the license to a dual license that U-boot supports. So we now have Embed TLS and LWIP, which are well tested and run in a bunch of devices to be responsible for our TCP and TLS stack. The bonus part and the reason we chose those 2 libraries wasn't random. LWIP already had support for Embed TLS, so eventually wiring up the HTTPS support was kind of trivial. We updated all the tools so you can add URLs and everything to add HTTPS, and you don't need those 5 different commands anymore, right? You add the boot option, and everything under the hood happens automatically. There are some pitfalls. So the usual one is that set variable at runtime is always a pain, and it's always going to remain a pain because of how the spec is designed. You need it for capsule updates, you need it for the distro installers, because what they do once they finish up the installation is set your first boot option to point at C. That's what distro installers typically do. You need to enable or disable secure boot, and you need to change the boot order. As we said, the set variable at runtime when you have an RPMB backend works perfectly fine if you have Linux. It's generally problematic because the assumption is that you have a flash that always remains under the control of the firmware, right? And if that flash, so if it's a file, that's not under the control of the firmware. SPI flashes are usually part of the non-secure world and delegated to Linux. The RPMB is obviously, and the eMMC and all the partitions are obviously being delegated into Linux. Servers sort this because they simply have a dedicated flash that is always under the control of the firmware, right? But for embedded boards, as long as a manufacturer doesn't come up with a device that says, this secure SPI flash is dedicated for variables, we always have to cut corners and figure this out. So set variable at runtime, in essence, is a part of the firmware that survives your boot, and the OS maps it and can run that code. For the RPMB, we believe it's elegant enough, I don't know, but Opti has a bus, basically, and we expose it as a discoverable device on that bus. So once the kernel comes up, scans Opti, scans the device, and goes, Opti can handle my EFI variables. Let me switch over all my callbacks to the EFI world to the Opti-provided functions. And this is completely seamless, right? Even the transition from a read-only EFI file system to a read-write is completely seamless. For variables stored on a file, this is less easy to sort, right? So what we ended up doing is we added generic functionality into U-boot, which applies to SPI flashes as well. So U-boot basically exposes 2 EFI variables that are read-only. One of them is the file name that you have to access and change in the ESP, and the other one is a binary dump of all the variables you need to preserve and write. So what we basically did is we went to the EFI var maintainers and we made this agreement that basically whenever we find these variables, we standardize that ABI, and EFI var basically copies the entire content of that special variable into the file. We've even tested this with SPI. I told you before that SPI is not supported for EFI variable at runtime. This is the missing piece. Because we tested doing it manually, it works perfectly fine. We can update the SPI contents from Linux. But unless it's in EFI var, you have to write a script or do it manually or do something like that. Eventually, we want to get it into EFI var and have this solution universally accepted. This is nice because The kernel doesn't really care about what happens on the context. He doesn't need to know the format of the variables or anything like that, right? It just looks at the file and writes it. The next one is HTTP support. So, back when we did this, we were starting installers, we were starting live images, and everything was working great up until to the point where we were trying to mount the root file system. Now, there's a point in time where EFI, the OS loader, basically, the kernel for us, calls exit boot services. That's the point in time in EFI where the device control transitions from the firmware to the OS. Now, it turns out that when this exit boot services happens, all the disks and everything you mounted from your installer disappear, right? So the installer moves on, can't find the medium, can't mount its image, can't continue the installation. Same thing happens with the live image. Distros had workarounds, right? So you had kernel command line options to point to a remote URL that contained your root file system, and you could continue the installer, but you don't need that anymore, right? Linux has PMEM, persistent memory nodes, which is very interesting for us because in one of the configurations, those act as persistent memory devices, block devices. So what we basically do in U-boot is that whenever we find that we're booting through HTTP, we mark that node as a PMEM node, Linux boots up, mounts it, and the installer, all the live image, just continues booting with basically no changes. So with all of the above combined, installing distrons becomes reality. I would like to write trivial, but you still have DT that's not in conformance with what the kernel expects or what the upstream expects. Your distro of choice hasn't enabled kernel modules or anything you need, or your vendor hasn't upstreamed these modules yet. But I think we're slowly getting there. EFI config and EFI debug are your configuration tool of choice. So this is, for example, how you add the live image, right? And I've used the EFI debug there to show the usage because I have a... Is it visible? Do you have Googles for the participants? Next year. All right, if it's not visible, I'll stop it. You can look it at the presentation, but this is basically the EFI config tool, right? You add your file, you add an HTTP URL, you tell U-boot to, this is your first boot option and this is the first thing you can boot, and then reboot. And you end up loading this is the live image, right? And the same thing happens with your OS. So if you install your OS or if you run your OS installer, you can do the same thing. Now, it's important that the EFI spec has a naming, right? So the EFI spec says that if I find this EFI application under a certain name in the ESP, you don't have to add any boot options for me to boot. I'll just boot the default file. So if you're booting an installer, you don't really need that, right? Just copy your installer in a USB and plug it in. It will start. But same example. Unfortunately, it doesn't show up, but basically, this is a board that boots Debian that's already pre-installed and boots upstream Debian with basically no changes. Thank you.
Thank you. Did you investigate the use of unified kernel images for having a recent device tree to solve some of the problems you described in the end?
I don't have... yes, UKI's work, right? It's above,
Yes.
above the whole problem. So if you boot systemd as your EFI application, systemd is responsible for the unified kernel images. It doesn't make any difference, right? So authenticating the device tree, etc., that's fine. You can do it through UKIs.
I was meaning like using a kernel from the UKI instead of a kernel from U-boot, because if it's out of date, like you said, then you can have a problem.
You mean device tree?
Yes.
Okay, the device tree. Yeah, so that's again, we've tried this, right? But U-boot nowadays has a config option that says, ignore all of the downstream device trees I've been carrying, just use an upstream one. That works fine. You can override the device tree that U-boot has and load your own. That also works fine, right? But The point is that eventually I want us to move away from this. I don't want U-boot to carry any local device trees. I don't think it makes any sense, right? And the kernel is not the source of truth for the device tree. It's where we decided that we should commit our device trees.
Thanks.
What does a basically unmodified Debian live image mean? What,
Sorry, what?
the basically unmodified Debian live image, you said it can do... It's completely unmodified. Thanks.
Yeah, it's completely unmodified, right? That's a disk I just downloaded off the internet. You have to make no changes. I mean, your only limitation is, do I have enough DRAM? With AI, this is becoming a problem, but that's the only limitation now.
The HTTPS booting option will it have some API that the binary can use to boot external?
So yes, we do have support for the EFI HTTP protocol. So you can interface with the HTTP layer through an EFI application. That's fine.
Okay, so people can theoretically build a UEFI graphical interface to boot it. Okay.
Yes. So there is support for the Simple Network Protocol. I think the HTTP protocol is also supported. So you can build an EFI application doing the same thing.
You said, I think, measuring device trees is not part of the standard right now.
Yes.
Are you gonna propose that it is? Okay.
So conceptually, it's not much different, right? It's both are describing the hardware, both ACPI, and they're mutually, at least in the kernel, we treat them as mutually exclusive, right? We don't have a device configuration where we can have both. So I don't think it even needs adding, or I don't even think that that spec needs a lot of changes. It just has to say ACPI or DT instead of just ACPI, right? Conceptually, it's the same thing.
Thanks.
Some devices are still using NAND memory, and GPT is not supported on NAND memory. Is it possible to have ESP on NAND, and is it possible to have UEFI boots?
Yes, and that's a common misunderstanding. That's a common misread of the EFI spec, right? The EFI spec says that your file system can be any file system, and here's an example on FAT32, right? Now, so I don't understand how everyone reading it just assumed that the ESP has to be FAT32. You can add whatever file system you want on the ESP partition, right? Apple uses a different one. I think, I don't remember who else. They use a completely different partition file system on the ESP. So,
okay, so does U-boot support ESP partition on UB?
We haven't tried UB, but I think you can try. We've tried VFAT, we've tried X4, we've tried a bunch of file systems that we have support, but I don't think you'll have a problem with UB. There's nothing in the code that prevents you from, there's no checks that says this has to be this file system.
Okay, just GPT partition I use today, so it does not exist on UB, so there are plenty of code to write. I expect to be able to do that.
Yes.
Yeah, I've been looking at implementing something like this that I noticed that in the standard boot for EFI, the device tree is currently expected to be in the EFI partition, but we have a customer that's wanting to put the device tree in the SPI-NOR.
Okay, that's a difference, right? Right now, this is the EFI, but this is the EFI subsystem, right? And the way to put that is through the EFI config and boot EFI commands. Now, in that thing, you can basically put your device tree anywhere you want. I don't know what the standard boot does because I haven't looked too much at it, because I think that, from memory, standard boot tries to boot with various different methods. So where standard boot chooses its device tree for EFI is standard boot's problem, and we can discuss it. But I don't know how to answer that because that's not part of the EFI stuff, right?
Okay.
It's a completely different boot flow, and if a functionality is missing, by all means, let's look at it.
Sure.
Hello, thanks for the talk. I would like to know how does the key provisioning work if I want to use the RPMB? Is the key provisioned by Opti
Okay.
or UEFI
Yeah,
itself?
that's a good question. No, the key is provisioned by the RPMB. The Opti is responsible for, the RPMB key is provisioned by Opti.
Okay.
Opti is responsible for writing it. That depends on the device, right? There's devices where we don't have a key and we write a default one, and we want to get rid of that for obvious reasons. There is devices where they have a flash in the secure world that they read the key, a fuse, and it's unique per device, which is the right approach, and Opti reads it and programs it directly on the first boot if there's no RPMB key. So it's kind of hardware dependent. Some vendors have already solved it on Opti.
But I think the take is there is no way to provision the key without Opti in the first place.
There is, but you can.
I mean, that would be manually, right? It would be manually, you
Yes.
would manually
U-Boot
provide.
I think U-Boot has a command line functionality to write an RPMB key if you want on an eMMC, right? The advantage of Opti is that, for what it's worth, everything remains isolated on the secure world, right? The key accesses, the encryption, everything we do, the rollbacks that we look at, etc., everything remains protected from the entire system.
Yep, thanks.
Next speaker up. More question here. I think Marek was. Did you have another question, Marek? Okay, we'll do a. Come on up and.
Continuing the question of one of my colleagues, if we measure DT, would you measure it before DT fix up or after?
Okay, so that's a good question. What we do now is we measure it before any fix-ups, if I remember correctly, and that's what the spec says about ACPI as well. Now, the reasoning behind that is that, in theory, in a product, you've signed your U-Boot, you've signed everything, you trust the binary to do any fix-ups, right? And you only load, you have Secure Boot enabled, so if there's any external EFI application that does fix-ups, you trust that as well. So the goal is to measure an unmodified device tree before any changes.
All right, thanks, Eliash. Okay, we'll get started with our next speaker. We'll welcome Kendall to the stage, and then we'll have a break after this talk.
Hi everyone, my name is Kendall Willis, and this is my presentation on mastering wake-up sources in Linux, architecture, APIs, and constraints. So a little bit about Texas Instruments is that we're an upstream first company. We really care about contributing to open source projects such as Linux, U-Boot, and Yocto. So a bit about me is that I'm a software engineer at Texas Instruments out of Dallas, Texas, USA. I'm specifically a Linux developer for power management on our general purpose Satara embedded processors. So the overview for this talk is that we'll first talk about Linux system suspend states. Then we will go over how power domains and wake-up sources interact. Then we'll talk about configuring wake-up sources, and then what the suspend and resume flow is for the wake-up architecture, and then runtime wake-up source interactions and maybe some gaps that are in the wake-up architecture. So first, let's start off with why does power matter on embedded devices? Firstly, a lot of embedded devices are in battery-operated devices, and for that, it is of the utmost importance to preserve battery life. Another reason is that lower power leads to more cost savings, and then also there have been some energy efficiency standards that have gone into effect in the USA and EU for household appliances, so that's something else to keep in mind. So, okay. First, let's go through the Linux system suspend states. In Linux, there are 4 broad system suspend states with varying ranges of power savings. In general, when you have a system suspend state that has more power savings, it will have a higher resume latency to get from a low power state to an active state. In Linux specifically, there is suspend to idle, standby, suspend to RAM, and hibernate. These states kind of build off of each other, so suspend to idle freezes user space, suspends timekeeping, and suspends IOs. Standby offlines non-boot CPUs in addition to what suspend to idle does. Suspend to RAM suspends devices and puts memory into self-refresh. And then during hibernate, everything is basically powered down but the wake-up sources. Today, we will be focusing on suspend to RAM when we're talking about the wake-up architecture. So now we're gonna do an overview of the Linux system suspend and resume flow. So once we enter suspend flow, basically the device power manager framework, or DPM, takes over and coordinates between 4 phases, which are prepare, suspend, suspend late, and suspend no IRQ. During these phases, devices might have specific configurations that they need to enact in order to suspend properly, or maybe to configure wake-up sources or wake IRQs, and that's done through hooks or callbacks for each particular phase. So for the suspend phase, we have the prepare, suspend, so let's go through each phase of the suspend flow, which we have prepare. During this phase, basically we stop registering any new devices, so no more can be registered and we can keep that down. Then we do suspend, which each device will basically be able to configure suspend how they are needed to. And then suspend late does the same thing, but just at a later phase. This will happen when runtime PM has been suspended, so if any drivers need to do any logic after runtime PM is suspended, it would be done here. And then during suspend no IRQ, all IRQs except for wake IRQs are suspended, and any logic that needs to happen after IRQs are suspended would happen here. And then afterwards, once we're in a low power state and then a wake up event happens, when we go into resume, basically we want to undo all of the work that we just did to get into a suspend state. So we also have 4 phases here, and they are basically mirrors of the suspend phases, but they undo everything. So we have resume no IRQ, resume early, resume incomplete. So now let's talk about power domains and wake-up sources. So this is an example SOC design where we have 3 power domains: the wake-up domain, main domain, and MCU domain. This is pretty basic, so we can get like a good idea of how these interact. But let's say that we have a wake-up source in the wake-up domain and a wake-up source in the MCU domain. So now if we go to a low power state, the main domain and MCU domain is off, but the wake-up domain is on. So if we wanted to use a wake-up source, we could only use the wake-up source in the wake-up domain because that is still on, whereas in the MCU domain, it is off. So another configuration that can happen is we can still have the MCU domain as off, but we can have the wake-up source 2 in the MCU domain as a wake-up source to wake up the system. This is done through something called like out-of-band wake-up, where maybe the wake-up source 2 has some internal hardware logic that keeps it in a state that can wake up the system. Another possibility is that wake-up source 2 could be IO daisy chain to another device, where basically the other device is still on, so it can still send wake-up signals that way. So how can we configure wake-up sources in Linux? Well, first, let's start with the device tree. We need to add the wake-up source device tree property to our device node that we want to be a wake-up source. From there, the driver would basically determine how the wake-up source would be configured, but this at least tells the driver that, hey, this device is a wake-up source. And then optionally, we can also add the wake up string to interrupt names. This tells the driver that there is a dedicated wake interrupt that can be used to wake up the system. So this interrupt would be different than the interrupt that we're using when we're in an active state, which if we don't have the string would be also the wake IRQ. But at the end of the day, the driver gets to decide how it uses this information. So let's talk about some structs that are used for power management. So first we have dev PM info. This struct basically just keeps track of any statistics or anything needed to coordinate power management. This struct is a part of the device struct. So any new device will have dev PM info included with it. So I've highlighted some variables that are important to us when we're talking about wake up, which is can wake up, which means that the device is able to be a wake up source. Wake up path, which means the device is either a wake up source or is the parent of a wake up source. And then out of band wake up, which means the device can be turned off, but it is still a wake up source. We also have the wake up source struct itself. This struct has different event tracking that can be used. It also has the wake IRQ struct. Dev PM info, it's not shown on here, but it also has a wake IRQ struct, so there's two places where that can be found. So let's go over some APIs for how we can configure these wake up sources in the device driver. First we have device set wake up capable. This just marks a device as wake up capable, but not necessarily enabled to wake up the system. This is usually done during probe. And then we have device set wake up enable. So if this is true, then it creates and enables the wake up source struct. Drivers are not necessarily expected to call this function because a device can be enabled or disabled through sysfs during runtime, but it can be used if there's some condition that the device uses to enable wake up or disable it. So on the side here, I just have some example code of like a probe where we read that the wake up source is in the device tree, and then we set the device wake up capable depending on that, and then during suspend and resume, we just set the device for wake up enabled or disabled. Now we have the device init wake up, which just basically combines the previous two functions that we just talked about. This is usually in the device probe, and this will just set everything up. So in the example code below, you can see that if the device tree property wake up source is present, this will be called for an example driver. If not, the device can just be set as wake up capable too. So now let's talk about configuring wake IRQs. Wake IRQs can be configured in a lot of different ways in the driver, but at the very least for a wake IRQ to be recognized, the IRQD wake up state flag needs to be set on the IRQ. So let's go through some functions that we can use during probe to do this. Dev PM set wake IRQ just attaches the wake IRQ to the wake up source struct. This does not enable this flag that we just talked about. Dev PM set dedicated wake IRQ does the same thing, but it is for a dedicated IRQ, kind of like the one that we talked about when we were setting up the device tree. This will also configure a separate handle threaded wake IRQ handler, which wakes the device upon the IRQ firing. If both of these functions are optional and you don't have to use either, but if you don't, and if you don't set up the wake IRQ struct, then you need to use enable IRQ wake during suspend and resume. This actually sets the IRQD wake up state flag. The reason that this needs to, or the reason that if we have one of the other two functions already set up during probe, like the reason that we don't have to use enable IRQ wake during suspend resume is that the device power manager framework already does it automatically for any wake IRQs that are connected to a wake up source. So it's basically one or the other that you do. Some other flags to consider for IRQs is IRQF no suspend. This, when added as a flag to an interrupt, it means that the interrupt does not suspend during the suspend flow, but it is also not a wake IRQ at the same time. This is usually used for important IRQs, such as timers that need to be processed during suspend no IRQ. And then obviously, when the system goes into a low power state, the handler still doesn't run, but basically it runs until the low power state is entered. Then we have IRQF cond suspend, which is basically a flag that happens for wake-up devices that have a shared IRQ line with a device that uses IRQF no suspend. Basically, this says that this is a wake-up source, and the handler must have logic in it to understand if the interrupt that it received was for the IRQF no suspend device, or if it was a genuine wake-up IRQ. There's also some IRQ chip flags that we need to consider, which basically the hardware interrupt controllers may need to explicitly configure which interrupts can wake up the system, and this is set up during IRQ set wake callback. Wake enabled and wake active are variables for the IRQ chip, which are used to keep track of the IRQ chip wake up sources. So we'll go through these three flags that are down at the bottom here, which are IRQ chip, enable wake up on suspend. This enables any wake IRQs that were disabled during the active state, so it will be enabled during suspend. And then IRQ chip mask on suspend. This masks all interrupts at the IRQ chip level during suspend. And then IRQ chip skip set wake. This will just skip the IRQ set wake callback. This happens if there is no particular hardware configuration that needs to be done in order to set up the wake IRQs. So now let's do the suspend flow for the wake up sources and see what happens. So starting off with prepare, not much happens here except for outband wake up and the wake up path are set to false for all devices. So let's say that you set one of these variables to true in probe, it will be overwritten. So that's one thing to keep in mind. And then there's suspend, and this has some logic in it. So first what suspend does is it checks if the wake up is pending, which means a wake IRQ has been fired during the suspend process, but before we have actually entered a low power state. If a wake IRQ has gone off during this time, then we abort suspend since we had an early wake up event. If not, we enter the suspend hooks, and then after that, we check if any of the devices may wake up. If so, we set the wake up path to true for that device and for its parent devices. So what wake up path will do is it will make sure that that device and its parent devices aren't turned off during suspend so that they can receive a wake up signal and send a wake up signal. And then we'll look more into the device driver suspend hooks that we were just talking about. So again, here is where you might need to set up any wake up configuration needed or any configuration needed for the device to enter suspend gracefully. We would set out of band wake up here if necessary. And then again, if necessary, we would enable IRQ wake here if neither of those dev PM functions were set before, the dev PM set wake IRQ or dev PM set dedicated wake IRQ. So at the bottom is just some code that's an example of a device driver doing this, which is device may wake up, then it enables the IRQ wake. So DPM suspend late does literally the same thing as suspend, but just during suspend late. So same logic there. And then during suspend no IRQ, we have several things happening. This function first arms the wake IRQs, so it enables IRQs if a wake IRQ is a dedicated wake IRQ, but it has not been enabled yet. And then it enables all wake IRQs by setting the IRQD wake up state. So this will lead into the next function where we suspend all IRQs. So when we suspend all IRQs but the wake IRQs and IRQF no suspend IRQs are suspended. Then for any IRQs with the IRQD wake up state flag, we also set IRQD wake up armed, which basically says this is a valid wake IRQ, and we are about to go into a low power state. So basically, it's not going to make the system abort suspending anymore. And then if any IRQ for the IRQ chip should be enabled upon suspend, those IRQs will be enabled. Then we will disable all other IRQs. After that, the suspend no IRQ hooks are called, and GenPD suspends devices and power domains. So if a device is a wake-up, during GenPD suspending the devices, it will check if a device is a wake-up source or in the wake-up path, and the device and its power domain will not be suspended if the wake-up source, if the device is a wake-up source. Depending on the platform you're using, this could make it so that your system is prevented from entering a low power state. But again, this is very platform specific and device specific, so that would be something that you would have to look up in the platform documentation. So just going over what happens if an IRQ fires before suspend no IRQ. For a wake IRQ, the handler would be called and processed, and then it would basically make the suspend abort. For a regular IRQ, handler is called and processed like normal until suspend no IRQ, and then after that it's turned off. And then for IRQF no suspend, handler is called and processed all throughout this process, or all throughout suspend, and it does not abort suspend. And then down here is some code from a driver that shows the handler, which is for a wake-up source. And basically, it reports a PM wake-up event to the system. So it tells it to abort suspend if we are before suspend no IRQ. So now let's talk about the resume flow for wake-up sources. So after suspend no IRQ, we have entered a low power state. And then a wake IRQ fires. So a wake-up event happens, and now we have to resume. So once the wake IRQ fires, IRQ can handle PM will run, and from there it will see that it was a wake IRQ and run IRQ PM handle wake up. During this, it will clear IRQD wake up armed, and then it will set that IRQ state to pending and suspended. The IRQ will be disabled, and the wake IRQ number will be recorded so the system knows what woke up the system. And then we will enter resume. So one big thing to note is that the actual wake IRQ handler for that device will not run at this moment because this IRQ PM handle wake up has set the IRQ state to pending and suspended. So now we're entering the actual resume flow. We're doing resume no IRQ. During this, GenPD will power on the power domains and devices, and resume no IRQ callbacks will be called. Then we will enable all IRQs. So from the wake IRQs, IRQD wake up arm will be cleared. We will also disable those wake IRQs, and then we will enable all IRQs, including the wake IRQs. So this basically gives the wake IRQs a clean slate. And then here's where we resend the IRQ if it was pending. So if the wake IRQ woke up the system, here's where the handler to service the IRQ runs. And then after that, we disarm all wake IRQs, so we just clear the IRQD wake up state, and then we disable any dedicated wake IRQs. So now we have DPM resume early. During this, the only real thing that we have to talk about is the driver resume hooks. During here, we will disable any wake up configuration that was needed or any suspend configuration that was needed. We'll do anything that is needed to resume the device. Again, we will disable the wake IRQ if it was enabled previously in the suspend function. DPM resume does the exact same thing as resume early. And then now we have finished our suspend resume flow in Linux. So now let's talk about the runtime wake up source interactions. So during runtime, we can enable wake up sources. This is done through sysfs. So basically, it would be for the device sysfs entry under power and wake up. Once you enable a wake up source via sysfs, it will create the wake up source struct. create SysFS statistics and enable event tracking. It will also attach the wake IRQ if there is one. And then when you disable the wake up source via SysFS, it just does the opposite. So it'll remove the wake up source struct and unregister the wake up source globally. So down here, we have some code where we echo enabled into a USB wake up source, and then we can see that it is now enabled. You can do the same thing to disable the wake up source, but echo disabled. And then how can we check what woke up the system? So we can look at all IRQs after suspend resume to confirm the wake up source. This would be done by looking at /proc/interrupts. So likely what you would do is before entering suspend, you would look at /proc/interrupts, and then afterwards you would look at it again and confirm which wake up source. This can be basically like a little too general. So another thing we can do is we can look at the wake up source statistics in debugfs. This will give a lot more different statistics that the wake up sources use, and it will list all wake up sources for the system. We can also look at the device specific wake up count, which is in the same place where you would enable or disable the wake up source. We can also find the overall system count from /sys/power wake up count. So those are a couple of the ways that we can confirm how we woke up the system in user space. And then now I'll talk about some gaps in the wake up architecture. So as we talked about out of band wake up, this feature has actually only been in the kernel for less than a year. Basically, this is just a flag, and there hasn't been any more work done for any other considerations, such as like, what if the device that is using the driver or has out of band wake up feature, but other devices that use the same driver don't? Or what if the out of band wake up needs extra configuration on top of that? So a solution to this would just be adding like a device tree property to say, hey, this device also has out of band wake up functionality. So then the device driver could basically use that device tree property and decide what to do based off of that. So during suspend, it might be like, hey, is this device tree property here? If so, let's set out of band wake up. So for an example for this, we have the OMAP 8250 UART driver where this was set up. On TI K3 devices, the UART has IO daisy chaining. So basically it uses device set out of band wake up, and some pin control is needed to enable the IO daisy chaining. So it also has extra configuration that is needed to set this up. Luckily for this driver, I was able to just add device set out of band wake up on suspend, but for other drivers, that would not be possible. So in summary, for the wake up architecture, first we need to make sure that the wake up source is on during the low power mode that we want to enter. And we need to take note of any special configurations that are needed for this. And then the device driver decides how to set up the wake up source and the wake IRQs at the end of the day. So the wake up source device tree property is needed for this, but you should check the driver to see what it is exactly doing. And then during suspend, any wake up source configuration is enabled during the device suspend hook if it has not been enabled during probe. And also wake IRQs are enabled and all other IRQs are disabled. So really, we need to make sure that the wake IRQs are set up correctly in the device driver so that it does get turned on, or it does get armed during suspend. And then once a wake IRQ is triggered and wakes up the system, the IRQ is set as pending and is suspended. And then during resume, once all IRQs are enabled, the handler of the wake IRQ that was triggered runs. All wake IRQs are disarmed, and any wake up source configuration is disabled in the device resume hook. So here are some references. Thank you.
Thank you for your talk. I have a small question. How to handle spurious wake-up events? The example, I have a laptop with very sensitive touchpad. When I close lid makes event to suspend, and my finger so close to touchpad, which makes wake event.
So, like, are you?
I don't want to have that wake event aborting the suspend flow. So how to handle spurious wake-up events?
So for that, that would be probably like a device driver handling. So like one option would be like maybe during the wake IRQ handler, you would basically check how long, or sorry, let me think about this for a second. But I think it would be more of like a device driver situation where you would have to check for the spurious wake-ups during the suspend hook, because basically, sorry, not the suspend hook, the handler, because basically the handler would run, and usually that's what aborts the suspend sequence. So you might have to add some logic in there to be like, if it is running maybe within this time frame, like to ignore it and not send the spurious wake up. But yeah, that would be a device driver situation.
Thanks for your talk. I have a question more related to platform integration. So I can see how at the end of the suspend process that you described, you would typically call in something like TFA to actually put the DRAM into self-refresh. But from your talk, I get the impression that the wake-up IRQ handler is directly received by the kernel. And so at that point, the RAM would still be in self-refresh, right? So my question is, how do you sort of coordinate to make sure that there is something to put the DRAM back in working state before you can actually run the kernel code that runs on DRAM, right? So could you comment a bit on the kind of platform integration?
That would all happen within firmware for DRAM. Sorry. Basically. Yeah, sorry. That should all happen within firmware. So the kernel doesn't really need to worry about that. It's just like for the system suspend states, when we're saying exactly what it should do, it's more that Linux has like set out basically like this is how the platform should work during like suspend RAM, but at the end of the day, that is the platform's responsibility in firmware for that to happen. So like if you wanted to do something else, you could, but you shouldn't, because that's not what the kernel's expecting.
So do you mean like the wake-up IRQ is first like caught by the TFA, for example, it will put the DRAM back in state and then sort of have Linux handle the IRQ in a second step or something like this?
Yeah, so basically like the firmware, I'm assuming like a wake IRQ would happen like a wake event, and then it would send that to the kernel. But like before that happens and before it gets to the kernel, that's where TFA would basically put the DRAM back into like an active state.
Okay, thanks.
Mm-hmm.
I have a motto that I like to say, that if we can measure it, we can understand it. So I'm wondering what kind of tools you use to measure, like when you implement something like this, what do you do to make sure it's working the way you actually wanted it to work?
So like for wake-up sources, if we're not measuring resume latency, it would be something where like, again, you would check like the interrupts in sysfs to make sure that it was working correctly, or like maybe you add in some trace to see either in like firmware or the like Linux kernel to see what's going on and like what wake IRQs have gone off. So luckily the kernel does have like a lot of statistics for that, where there's like the debug FS that can show you what happened and then the wake IRQs. But yeah, so like using something like trace to see what wake IRQ woke up the system.
Great, thanks.
So you've described it as being a list of wake-up sources that you can pick from. but I know on your TI platforms, some are not accessible based on which suspend type you're going to be using. Can you talk a bit about how you support that, and if you have any plans on improving the support in the kernel, which isn't that great at the moment?
Gotcha. Yeah, so for TI specific platforms, like you said, for Suspend RAM, we have quite a few different low power states, and they're described like in our documentation, but in the kernel, we don't really have like a way that shows which wake up sources we're using. But like one thing is for like our TI K3 devices, there's QoS constraints that we use. So basically, if a wake up source is on that is used for like, let's say, deep sleep, which is one of our low power states, we will make sure that we enter let me go back a little bit. So we have a wake up source that's available for deep sleep, but like for something like partial IO, it's not available. So if the wake up source is enabled in the kernel, it will only enter deep sleep, but if it was disabled, you could enter partial IO. So that's kind of what I was talking about earlier when I was saying that depending on your wake up source, if it's on, it might not allow you to enter a certain low power state. So yeah, we don't have it super clear, I guess, in the kernel, but that's kind of the way that we do it, is that we have QoS constraints where we check that during suspend through our TI power domain.
And so you change if a device is wake up capable during the suspend callback itself?
Yeah, so it's during what happens is the TI power domain driver will check and see which wake up source, if there's any wake up source constraints. Those constraints they'll be set during, I have to double check on when they're set.
Yeah, no worries, okay.
Yeah. But basically those will be set when we have a wake up source. So it'll basically be like, okay, this wake up source has to be on. It tells the firmware that it has to be on. So the firmware will choose the state based off of that, and it'll choose the deepest state available.
And would there be any plans to have an API from user space to be able to give user space the choice of saying, I want this precise sleep? Because at the moment, user space says, oh yeah, I might be waking up with that latency on that wake up source, and it's hard for user to say that and then be certain that you will pick the right state. Because the danger is if your system goes into the wrong one, it's super lightweight and you make no power savings.
Right. So for our AM62L device, we have something kind of similar to that where we've made S2 idle states where basically you can choose which low power state to go into based off of some latency that you choose. And yeah, so that's how we do it on our newer ones. For like our older K3 platforms, we don't have any plans to integrate that. For our newer ones, it is a lot easier to tell which one you're going into because you're basically saying, hey, this is the latency constraint we have, so you can reasonably expect that it will go into that certain low power state.
Thank you.
I'm still alive. So you mentioned latency quite a few times. How do you actually measure from, I don't know, some wake-up event like a user tapping something or whatever, the time that it takes before everything's running properly again and it's as if you never slept?
Yeah, so for measuring resume latency, you can do that in several different ways. Like one way you could do is if you were to add like maybe a GPIO signal in your firmware to say, okay, this is like the first step where we're woken up, and then you can add another signal during Linux resume to say this is like the last step. So you can kind of measure that way. That's one way to do it. There's some trace tools that you can use. Yeah, so there's several different ways to do that. GPIO signaling makes it so that it's pretty accurate.
I saw one more hand. No, looks like we're good. Everybody's ready for lunch, I think. All right, well, thank you, Kendall. To take a break for lunch. Lunch is outside, like I mentioned, so out behind here, to follow some signs for lunch. You can take your lunch anywhere in the park. There's a fair amount of seating where the lunch is served, but there's not enough for everybody. But there's benches all over the park. Hopefully you can find a place that's shady and enjoy your lunch. So we'll be back here in a little bit more than an hour and a half. 1:30 we'll be back here to start off again. So enjoy your lunch. Bon appétit.
open source project.
Check, check. Hello, hello. Welcome back. Find your seats. We're going to get started again. I hope you enjoyed a good lunch, and a little bit of sunshine. Hopefully more shade than sunshine. I found the slide that I missed this morning, so I have it up here, so hopefully you can read. But for tonight is the evening social event. The important thing is make sure you bring your badge. The little red dots on your badge are for everybody that signed up for the evening social event. So if you have a red dot on your badge, that means you get into the beach club tonight. So make sure you bring your badge, and you can go to the website to find the address. It's a bit of a walk, but it's also right on the tram line. So look forward to seeing you tonight for the evening social event. And with that, I'm going to call up our next speaker and get rolling again.
Okay, good. Let's get started. I only have 15 minutes and a stack full of slides, so I get right into it. So I'm Michael, and I'm talking about Ares Init. It's a small, tiny init ramifest toolbox for embedded systems. A few words about myself. I'm an embedded Linux developer at Pengutronics since 2006, so for quite some time. And I'm the team lead of the graphics team there. So why an init ramifest toolbox? So historically, at least from my perspective, in embedded Linux, we didn't use init ramifest at all in most cases, because the root file system was mounted easily. It was always the same device. There is no complexity there, and just leaving init ramifest away, it just makes it easier, and that's what we did for a long time. But nowadays, we have more requirements. We have integrity requirements for the root file system, so we use DM integrity, DM Verity, and while the kernel can mount that specifically directly, there are often other additional requirements like encryption, or if you actually want to develop with that, and I come into detail what that means and what we can do there, it gets a bit more complex, and so I started looking into what can we do there for the init ramifest. So what are my requirements? Well, first of all, I wanted something with a minimal overhead, and that means size, and that also implies time, basically. I did a talk at ELCE last year, measuring boot times with Secure Boot, and one thing that I noticed was if you get a larger init ramifest, that really adds extra time, and I wanted to avoid that. And since we're doing a lot of Secure Boot and these verified boot kind of things, we want to do something that's robust and secure. So if we add this extra layer in our boot chain, it should not add additional security issues. And I wanted to have something that's extensible, because there are always extra use cases that have this one specific feature that they need. And if it's not extensible, that means for every use case, either someone is carrying patches, or it needs to integrate all these kind of features in the main implementation, and that's not so nice as well. So the first thing I did was, of course, look at existing stuff. And that means basically, for the most part, the Yocto init ramifest framework, because it's there. You can just use it if you use Yocto. And I think for most people, something like that is always a good case, because you don't have to do something new, you don't have to integrate something new, and so that helps. It's extensible. I mean, I don't know who knows the details about it, but it's basically just a bunch of shell scripts, and you can insert your own shell script that's executed as well. But it gets pretty large in size, a few megabytes typically. And I said that's something I don't like. And it's shell scripts. And when it comes to security and robustness and error handling, shell scripts, well, you can get it right, but it's hard. So I wanted to avoid that. And I looked a bit around as well with other stuff, but there's nothing that where I said, well, this looks like something that I want to use that fits my requirements. So, well, I started something new, and I did what all the cool kids do nowadays. I wrote it in Rust. Mainly because I wanted to have a compiled language, and Rust is a high-level language, so I don't need to all do with the fiddly bits like we would do in C, and it provides me with a lot of help for security and error handling and these kind of things. Okay, so when I built the whole thing, I decided, okay, what am I going to do with it? What's my vision? Where I want to go when I decide what to add and what not to add? And as I said before, and say again, it's supposed to be small. So when I look at new features, I really try to see what can I do to keep things minimal. Because with Rust, you can also easily add a lot of new stuff, get a large binary by just using this crate and that crate, and here's another helper, and then you add a lot of dependencies and a lot of stuff in size, and that's something I wanted to avoid. And I want to do it entirely in Rust, especially without any C libraries and their bindings, because it makes it more difficult to build a single binary for an initramfs. This is not inside the root file system, so any C library either has to be built statically as well, specifically for the initramfs, or I need to add the C library as well on top of that. And so this is not the kind of situation I wanted to have. So as I said, for the basic stuff, what I integrate in this project directly, it's supposed to be Rust only. And I want to produce one binary from the crate itself that covers the basic use cases, so basically what the typical use cases are, but make it in a way that it can be integrated in your own Rust binary as basically a library to create your own init that has a few additional features on top of what this basic RSinit crate provides. So let's look into it, what actually can be done with it right now, and where I want to go with it. Well, first of all, we want to mount the root file system, of course. And for the most part, we start with what the kernel can already do. So basically, for the, let's say, all simple cases, if you provide kernel command lines that the kernel would be able to mount directly, most of that RSinit will mount transparently as well. So it helps with transitioning, and it helps with recognizing the kernel command line options, etc. So normal partitions work. The Inverity works as well. That's why I started the whole project, so that's in there, of course. Starting root file system from NFS for development, that's there as well. 9pfs, I don't know how many people have used it or know about it. Show of hands, maybe? Yeah, quite a few. So in QEMU, it's really nice to do that, to get a file system that's inside your emulated device and outside, so you can transfer files back and forth. But you can also use 9pfs over USB on a real device. Just need a USB device port on your device, attach that to a PC or your server or whatever, and then you can do USB 9p over USB. That requires some extra setup, and RSinit has support for that. It's really nice if you have a setup where you don't need, where you don't have networking, or you don't want to rely on networking for your root file system. Obviously, more to come. This project is pretty new, but that's the basics that we have right now for mounting. So for development, stuff like the Inverity makes things harder, because we cannot just no longer say, let's remount our file system writable and just copy a bunch of files to edit things, copy our binaries, test again, recompile, copy the binaries as well. So unless we have some way of doing a writable root file system, that would require rewriting the whole file system, and it takes longer. That makes development and debugging slower. So what I've started with in RSinit to provide helpers to make it possible to mount an overlay FS on top of the root file system right before the actual init starts, so it's transparently already there with everything, and then boot, and then later on it can still be mounted read-writable, and you can copy stuff on top, and either if it's a volatile overlay, it's gone the next time you boot, but if it's a persistent overlay from some kind of partition, then you can actually copy things onto that, reboot with your modifications, test these kind of things, and do that loop again and again. And as a bonus, if you just throw away the overlay, then you have the clear original root file system back, not something you had before when you start modifying your root file system again and again and again, and you don't know what are the local modifications and what was originally provided in your image. Okay. That's for that. So, and another thing is a feature for kernel developers. I don't know, I'm guessing that a few kernel developers are here. If you just do kernel development, then the typical use case would often be, I just want to replace my kernel, right? And my kernel modules. And again, we have the read-only root file system, and it makes things hard. So what my colleague came up with is, hey, if we can do a kernel, and we put the kernel modules in an init ramfs, and deploy just the kernel and the kernel modules together via networking like TFTP or NFS to the bootloader, load that kernel, use the original init ramfs from your system, add the additional init ramfs with the kernel modules, and you can concatenate init ramfs. You just chain them together, and the kernel will extract each one of them. And then RSinit will come and see, okay, I have this additional kernel command line. I'll look into the init ramfs, and if there are kernel modules that match the kernel that was just shorted, then these kernel modules are bind-mounted on top of the root file system, so you have suddenly your new kernel and the new kernel modules, and you can just do your development loop like that without modifying the root file system. And that makes it a lot easier, a lot faster to do these kind of kernel developments. There is a talk at FOSDEM that my colleague gave, Ahmad. I've put the link here, and he explained a bit more on what his vision was there. I think there are minor differences in the whole thing in terms of how the integration in RSinit works, because it was an earlier version of the merge request that he described there compared to what was merged in the end. Okay. Well, another thing I've looked at is read ahead. Read ahead basically as a method to reduce the boot time. Steve Rusted had a talk at ELCE, I don't know, 2 or 3 years ago, where he picked up this topic and explained how to use a trace event instead of kernel patches that the original implementation had. And what I did was take his idea and implement that in RSinit. Basically use the trace event to trace which blocks of the files are read at boot time, collect that into a file. This needs to be copied then manually and into your BSP, whatever, then added to the init ramfs. And with the next boot, if this file exists, RSinit can use that in combination with POSIX fadvice and will load these pages in background while the init is already starting, but it will queue the POSIX fadvice for all these files and their blocks, and so the content is already cached at the time when the applications actually need that part. In my test cases, there was about a 10% speed up in a really simple, trivial test case for just the user space part. So it's really something that makes sense, that helps with boot times. Right now, it's a draft PR. The implementation is pretty rough, especially the trace event handling is rather hackish. And I'm not quite sure how I want to integrate all of this, how to enable it. But it's there and something I want to finish at some point. And last, for the future. So it's obviously not finished. One thing that's not yet implemented, it's a bit on my roadmap, but so far I could convince the customers that brought this topic up that encrypted root file system is not really necessary, but I'm pretty sure that we'll get there somewhere. But encryption always has the issues with where the key comes from and these kind of things, so it's often a bit either hardware specific or project specific, so integration there will also be, well, we'll see. And as another topic, as final thing, boot splashes. The init RAMFS starts a bit earlier than the user space, so my hope is we can add something there and use that for all the customers. I think, ooh, it should be early, and can we do that in the bootloader? And I say, we don't want to do it in the bootloader, so let's put it in the init RAMFS, get a boot splash in there, and hope that's early enough for people, so that we can use that. Okay, and that's it. I'm out of time, and I don't think there's time for questions, but I'll be around in the conference for today and tomorrow, so if you have any, talk to me. Exactly on time.
Perfect. Right, yeah, for our short 15-minute lightning talks, we won't usually have time for Q&A, but it's just a good reason to go find them at the evening social event tonight. So I'll invite up Alex, our next speaker.
If this works. Yeah. Oh. All right, that works. All right, I'm Alex from Red Hat. You may know me more from my history of work in GNOME and Flatpak and Podman and things like that, but the last couple of years I've been working on automotive inside Red Hat, and I'm here to talk about how we do booting and how we think is the right way to boot and update an automotive system, right? So I work in the automotive team, and the goal of the automotive team is to make RHEL for Linux, or RHEL for cars a thing, right? RHEL is many things. It's the product, but it's also a project. So we have the same kind of layout. We have an upstream, automotive stream distribution based on CentOS Stream. It's all upstream. You can all look at it. You can use it. If you want to use it, you can of course, but maybe you just want to look at it and steal some ideas or whatnot. And then we have a downstream, the Red Hat in-vehicle operating system, which is the RHEL product. And we expect that to be something that third-party people, like car manufacturers, buy and put in their cars. And that's the thing we need to design then. How do we boot this? What kind of overall requirements do we have? Clearly, we want some kind of image-based operating system. We don't want to use packages and have updates. Different cars run the same version, but they upgrade it at different times and run scripts in different ways. Like, we need a single read-only version of each released image on your car. Right? It should be bitwise identical. It should validate that it's bitwise identical, kind of like DM-Verity, but we're not actually using that, as we will see. We also need robust updates. We need an update system. And your over-the-air updates should never, ever break your car. Like, that's basically, over-the-air updates is going to be more and more important for cars because cars are getting more and more complex. The in thing is something called software-defined vehicles. But it basically means that your car is a computer with wheels. So any update need to write to inert, like it should not affect the running system,
And at the end, you trigger an atomic update, you boot the new thing. If it succeeded, your over-the-air update was fine. If it didn't, it should detect so and fall back to the old thing that we didn't touch at all. Additionally, and this is not great for the open source story, but we really need a chain of trust that you can sign your entire set of code you run. Like you need to sign kernel, you sign in NetRamFS, sign rootfs. Everything needs to be, like you, basically, if you allow end users to manipulate your self-driving cars, it's gonna be bad. And also, and this is not always great, but we have to support whatever hardware our customers need. We're not really a huge company in this space, so we can't dictate requirements. On the other hand, like this is an embedded conference, and cars are, I guess, embedded, but they're way larger than your traditional old school. At least these software-defined vehicles, they're pretty hefty things running, machine learning stuff and all sorts of, we had an 8-core, 32 gigabytes Qualcomm machine, for example. Is that embedded? I mean, maybe. And the solution we came up with is called Bootsy. I'm sure many people have heard about Bootsy because it's also used for RHEL, where it's called image mode, and for Fedora, where it's things like Silverblue or Fedora CoreOS. And overall, I think other distros use Bootsy also. It's based on containers as a way, or container images as a way to deliver the image updates, right? So you build a container image and you upgrade your system either from an OCI archive, like a tarball, or directly from a registry. That gives you all sorts of advantages, like you can inspect your images, you can run them using Podman or whatever, you can deploy them using infrastructure your company already has, you can use existing tools to inspect them and whatnot, and it's very flexible. It has the right shape for what our requirements are, but there was a lot of tiny details, particularly about this verifications and stuff that wasn't quite there, that we had to work on. So let's take a look at the entire boot process and what we need to do here. We're given from some vendor some hardware that has a firmware. We can make some requirements on the firmware, but not overly harsh. And it has some kind of hardware key, and the firmware will validate the bootloader. And the bootloader will then validate the kernel in NetRamFS. And then that will have to mount the root file system and validate all the contents of that. In each part here, we have to look at. For firmware, we think in the long run, EFI is the way to go. It's generic, not tied to specific hardware. There are multiple implementations of it. It exists, it works. It works very well for x86, and it kind of works for ARM. It has secure boot, so there's a way to validate things. There's a standard way to sign things. People know it. However, in the embedded sphere, Android boot is also common. And in fact, we do have some boards that we are required to work with that supports only Android boot. But it has something called Android verified boot, which is similar to secure boot in the feature set. It has a custom format for like the boot partition that has the kernel and NetRamFS. So it kind of has the same shape. So these are the two we support. And then the next step is the bootloader. Actually, for Android boot, we don't really need a bootloader because it's kind of is already. Like it has boot counters, it has 2-slot system where AB boot updates. And we already worked on OS3, which is, the core part of Bootsy that does the image mode. It already has support for AB switching, so when you do an OS3 update, it deploys to the new partition, and when they boot the system, we get told by Android boot, what slot is in use, so we can use that to find the right OS3 commit to boot and things like that. So really, we don't need a bootloader on Android boot. But we do need one for EFI. EFI can only boot like a single file. We need something that we can add extra features to it. And for RHEL, like the solution is Grub, and that's obviously not going to work. There are smaller things that might work with for embedded, like system deboot or whatnot. But even those are kind of overly large and has like interaction and whatnot that we might not need. So instead, we wrote a new EFI bootloader called UKI boot. It's really a very thin re-implementation of the same workflow that Android boot has. So there's like 2 raw partitions where you dump your data that gets loaded. There's a UKI boot B A and a UKI boot B partition, and there's a UKI boot control partition that just has the boot counter, the active slot, and things like that. And that means we can use this on EFI and Android boot on Android boot, and the user space doesn't really have to care because it produced the same kind of kernel command lines to tell you what slot is active and whatnot. So it just slots into all the integration work we already did. And it's not really a large project, but it's really makes it really useful. So if someone is interested in using that, have a look at that. And then we come to the kernel and initramfs. And really what we need is all the parts that decides what you run. So it's the kernel, the initramfs, and the kernel command line, and the DTB if you have one, right? So there's already in Android boot a way to stuff this into one and sign it. So it's basically the A boot format for boot A and B. And there's a signature for it that you sign. On EFI, these are actually more like separate things. So we need to somehow make them into one format. Unfortunately, there is already existing work on this. It's called UKI, or Unified Kernel Images. It's from the UAPI system deboot people. And we're using their UKIFI tools and whatnot to create these. But the way they work is that you create like an EFI stub, and then you add a bunch of sections in it for all the different parts, and the stub knows to extract these and run the kernel when you boot them. And that means we have a single file we can sign with the EFI signature that causes us to trust the entire initramfs and kernel. And in the initramfs, we have kind of a minimal Dracut kind of initramfs with some custom things to make it small. But it has to have the OS3 integration because it doesn't just boot or mount the sysroot. It needs to find in the sysroot, because we're only using one root. There's not, in Android boot, you'd have 2 root file systems. But we only use one, and instead we find, in that one, we find the OS3 commit that we're about to mount. And then we mount that as the root and switch root into that. And here we have inside the initramfs a key that binds the initramfs with the rootfs. So basically, we sign the rootfs image and stuff with the like throwaway key that we build that we change for every build. So that way, we basically merge the rootfs and the initramfs. We call it sealing, and it's really useful because you really don't want your newest initramfs to be able to boot any old rootfs because they might have like security issues that require them to be updated. So basically, we make them one image. And I mentioned ComposeFS. It's a project I've been working on for a couple of years, I guess 5 years. I don't know how many people know about it. But it's the core of what makes OS3 work in a validated way. It's easiest to explain how it works by using the native ComposeFS tools and create an image and mount it. So here's a super simple rootfs. Obviously, a real one would be much larger, but that's basically what it is. It's a bunch of files. And you can create example.cfs here by pointing it at this, but you also give it an objects directory. And that will create your file, example.cfs, plus a bunch of content addressed files in this objects directory. And this has like a footer text and a border text, and the content in the files are in these separate things. And what happens here is that the example file is the image, except the content. So it has the names, the structure, the permissions, the M times, all the metadata that is in the image, but none of the content. So it's kind of a small thing. And then it references external files for all the objects. So you can mount it by specifying this base directory and the main file, and then you can just access it like a regular mount. And it's important to understand the role of this base directory. Like if you were to replace an object in there and mount it again, you changed what's in the content of that file. So this is kind of what we want to avoid, so we need to work on this anymore. But this explains why this is important, because the base directory can be shared, that it's not tied to one image. If you have two images, one being, say, the current version of your Buddha system, and the second one is the next version you're upgrading to, if only like 5 files changed, then all you have to do is write 5 new files in the base dir and the new main image, which is kind of small. And then you do the upgrade. And you can sort of understand that you can do the same thing on download as well. You can just traverse this thing and naturally know the delta you need to update. And so these are shared on disk. They're also shared in the page cache. That's not necessarily as important for the rootfs, but if you're using this for containers, which we're looking at as well, then if you have, say, 10 different containers, but they all have the same libc file, that libc file will be sharing one file in the backend directory, and therefore they'll all be using the same page cache for that. Basically, the page cache is inode based, and there's just one inode. So we were able to change a file and have that being read. That was exactly what we didn't want to do. And the way we fixed that is by using something called fsVerity. It's like the lesser-known cousin of dmVerity, but instead of on the block device scale, it works on the file scale. So you use a VFS operation basically to enable fsVerity on a file, and that makes the file immutable, and it appends like a Merkle tree, and then there's like a top-level hash for the Merkle tree. And every time you read a block, it gets validated against that Merkle tree. So if you ever, like you're not able to use the VFS API to modify the file, but for sure you can write to the block device, or maybe there's some like actual physical damage, or you read the wrong data, you will get told immediately the first time you use a block that it's corrupted. And if you go back to ComposeFS, you'd see that we actually enable fsVerity on all of these objects for this reason. And in fact, in the native ComposeFS repository format, the actual checksum is the fsVerity top-level hash. So if we mount with the option Verity on or Verity require, then it contains the expected digest in the metadata file. So every time you try to open a file and the backend file was changed, then it just complains to you, this is bad, something changed. And that way, we can trust the base directory files. Additionally, we need to trust the metadata file itself. So we enable fsVerity on it as well. And then we can measure it and pass the expected digest on the mount command line. And if it's not the right one, it will just complain and say, this is bullshit. So basically, that makes the fsVerity digest of the image a root of trust, similar to the top-level digest of a DMVerity partition. So what we want to do is we want to have some kind of trust in the InterMFS that we can pass on when we mount the root file system. And like, this is how it would look in an entire system. We have the hardware root of trust that signs the VB meta partition. This is Android boot. And that has a hash of the boot partition. So we validate the hash, and then we can trust the kernel and the InterMFS. We start the InterMFS. It has the per build key. After it mounts the root file system or the sysroot and finds the to-be mounted rootfs thing, it has a signature of it, it validates it, means we can trust the digest, means we can look at the rootfs.cfs file, make sure it has the right digest, then we can trust the image, and it has the expected digest for everything. So basically we have a flexible file-based system where we can trust the entire rootfs at like read level. When we use this in bootc, there are some changes. The examples I gave were using the MK ComposeFS tools that has its own repository format that is native to ComposeFS. In OS3, we use the library instead to work with the pre-existing OS3 repository format, but at the end of the day, it's basically the same thing, right? It's a repository, there's a bunch of Git style object files. And every single version, like every image we deploy, becomes a deploy in this deploy directory. And when we boot, we look at the current slot to find the root file system that was intended to go with that deployed slot. And there we have the ComposeFS file for the root file system, plus the OS3 commit for it that is signed with the key in the InterMFS. And then we can mount it as the root and pivot root into it, and we have a trusted system. There's some extra stuff for our use of OS3. Normally in OS3 systems, etc is persistent. There's actually this complicated system where user etc comes with the image and gets initialized, but then you change stuff, and when you upgrade, there's like a three-way style merge of the etc to the new etc. But we really don't need a writable etc, and we don't want one. We don't want, if anyone becomes root at the system, they shouldn't be able to modify etc to persist root access, basically. So var is really the only place for dynamic persistent data. So you'd have logs and map data or whatever in directories in var. So to build our images, we use a tool we created called Automotive Image Builder. I'd like to demo. I wrote demo, but I don't really want to build huge images on this machine in a demo. So I'm just going to show you some command lines, how it would work. This is a trivial manifest for the image builder. And this is the command line you'd use. This is a QEMU build. If you were building for hardware, you say like write for or something. And it builds a container image. So that's the resulting thing, is a container image. And you can look at it in Podman, it's just a container in the store. You can run stuff in it, you can inspect it, you can run whatever tools you have for containers, you can push it to a registry, pull it from a registry, and whatever you want. And the first time you want to boot it on a system, you need to use this command, to disk image. That converts to a physical disk, basically. You can create a raw file or a QCOW or whatever that you flash to your system or run in QEMU. But that's just the first time. Well, basically, it's like a physical instantiation of the container. Once you have that second thing booted, you can upgrade directly from a repository or from an OCI archive file. So that's the way to do. And for signing, we have tools in the builder. Basically, you build your regular container, And then you use the extract for signing thing, which knows what kind of boot you have, so it extracts the files you need to sign. And then here I just use SB sign, but in an actual real product, there's probably a really complicated way to send these files to some air-gapped computer where you can sign it or something. And then you get them back, and we can use the inject sign thing to create a new container, like the one labeled sign there, that has the signed file in it. And then we boot it by creating an image and running it with the automotive image runner. It's just a QEMU wrapper, actually. And we pass some EFI variables, so we enable secure boot and set a custom key and whatnot. And it seems to boot, and it validates the EFI stuff, but then it fails. That's not great. Does anyone have any idea what we did wrong? Actually, the fact that we signed the EFI modules means we changed the root file system. So the sealing stuff for the key pair and the signed root FSDI just isn't working anymore. So we need to reseal. So if you, for example, use bootc and create an image and then use Docker files to extend it, for example, which is something you can do, then you need to reseal the file at the end, or reseal the container, which basically involves stuffing in a new build key and re-signing the root FS. But the problem is that stuffing in the build key in an inter-FS, that invalidates the signature as well. So there's some kind of cyclic thing here, which unfortunately makes the real signing kind of painful. So you have to first generate a key, use the prepare reseal to stuff the one-time key into the init.fs. Then you extract the EFI files, sign them, and inject them. And you pass in this one-time key, and then you throw it away. And that way, you get a signed image, which we can boot. You can see, if you look in a journal, that the secure boot is enabled. I can actually, I have one here if you want to. I have some. Yes, out would look. You boot the system. You can see that the secure boot is enabled, so it validates everything. If you look at the root file system, it's a Compose FS, and etc is an overlay against like a transient etc. And actually, you can see with using the bootc commands, what's up? We're booting this particular version, and I did build a new version. So if we want to try to update, we can use bootc switch, which is basically bootc update, but when you specify an entire new. So bootc update would look for the same name of a container and pull it down, and if there's a new version. Switch is just side grade. But we can upgrade using OCI archives as well, and that's probably what will happen in most cases. Cars are not necessarily wired up, so you can just pull something from a registry on the network. It's more likely that you have some pre-existing update system that allows you to feed blobs to it, and those would be OCI archives. Or actually, I'm also working on an OCI Delta format where you can make deltas for upgrades between different OCI containers. That makes the symbol a lot smaller because This one is the entire thing. But now we have both installed, so we can see boot C status. So the one with the dot is the one that I have booted, and then I have a stage 1 with a new digest. So if I reboot here, it boots into slot B here. We can see UCAV boot B is loading UCAV from the B slot. And we're still in a secure boot environment, but we're in a new in the new version. But the old one is there, and if you look at the something. What's it called? Yeah, so if we reach boot completed successfully and everything works, we run the UKI boot set success. That marks the B slot as valid, and now if I were to reboot again, it will keep booting in boot slot B. But if it never reaches this, then after I think 6 boots, it will go back to slot B again and boot the previous version. And everything is like all the files are in those 3 repo objects, like we saw in the earlier demo. Like these are a bunch of files that represents the actual, or we can also the pro directory has a file .os3. Let's see this is the backend file, or the metadata file. So they're kind of small, 2 megs. We can you can see here all the files in it, or you can see all the data for it. Like the regular files or directories are just the data, but if you find one of the regular files here, you see the object files in the object directory that actually is used for the content of these files. I think that was it, maybe a bit early, but if anyone has questions, that would be cool. Here's some references to the stuff we're using. ComposeFS is the ComposeFS. There's actually also a ComposeFS-RS, which is a Rust rewrite of ComposeFS, which we think is the future of ComposeFS, that we are looking at using in the future. But UKIboot is the bootloader, and there's the builder, and aboot deploy is our integration in OS3 for Android boot. All right.
Yeah, I was wondering how much is the performance loss into ComposeFS plus signing and checking compared to more traditional file systems? Because we do have customers that want to go to the UI like in 5 seconds.
So I don't really have data on it, actually. I haven't done a lot of actual data. But in terms of what code gets run, the validation does cost some, like depending on your CPU performance. But if you compare it to dmVerity, you're basically doing the same thing. So I would say if you need validation, you're gonna have to bite that cost. And I wouldn't say that FSVerity is worse than dmVerity or really much different.
There you
go. Regarding UKI boots, so this is entirely homegrown, right? And it's also part of your verified boot train of trust. So how did you handle cryptographic primitives for this? Did you rewrite them yourself? Did you like reuse libraries from some other project?
No. There's no, like, UKI is like 1,500 lines of simple code to read file data from a partition and maybe from another partition. It doesn't do any of its own crypto. What happens is in the end, you loaded the UKI boot partition, it contains an EFI file. And if you use the EFI API to launch an EFI binary, that will trigger the whole secure boot mechanism.
Okay, so the UEFI firmware handles the, okay.
Did you look at EFI Bootguard as a bootloader implementation doing something very similar to you? Because also you do not have a watchdog in place, which is something that we provide at least for x86. Any ideas on that?
Yeah, I mean, we fundamentally require, at least for our safety critical use, an external watchdog for our hardware always. So I haven't really thought about software or using.
Okay, that's fine. If the firmware does basically the startup of the watchdog, then you are out of that part.
Yeah.
But did you look at the approach that we took for EFI Bootguard for selecting AB? You're not aware of it?
No, I haven't looked at
it. We can talk afterwards.
Yeah.
Sorry.
Okay. Which policy are you using to validate and mark the boot as successful?
Basically, we use systemd if you reach the boot completed.target, and then we have some place where you can easily add dependencies in front of boot completed or boot completed.
The default target.
That you can do whatever you want. Like if you have a script that returns false if something was not working, that will make systemd know that boot completed wasn't reached. And
thank you.
Then we won't mark it. We have on the server side something called Green Boot, which we're not actually using, but it's very similar to that.
Thank you, Alex, for your talk. Sorry, I maybe barely understand some concept. As I understand, you have the completely immutable system, and the only var directory is allowed to write, correct? So USR is protected from writing.
Yes, and the entire slash is protected.
Okay.
Including user.
Yeah, and
except var and.
Except var. And why do you use OS3 here? For what reason? Because as I understand the update.
I mean, we have to use something. So why do you use OS3 compared to, for example?
Yeah, because as I understand the concept of OS3 is that you can commit changes. So why you need the all OS3? Sorry, maybe it's a very silly question, but as I understand the updates is the full image in the B slot, right? So why the OS3 exists here?
No. What would be in Android boot be an entire new file system for root A and root B is in our case a full root file system for A and B that shared 90% of the files. That's what OS3 gives you basically.
Okay.
So when you do an update, you only add the additional content files that is new to this image, and then you can store 5 old versions if you want, and you can easily switch between them however you want.
So you do some kind of deduplication. So you only, when you update, you download the diff from the previous or not?
Yeah, the deduplication is happening automatically because the shared repository directory is content at rest. So like if you have a libc file in boot A or root A, and it's the same in root B, its checksum will be the same. So we'll use the same file in the repository for both images.
Okay, I get. Thanks. Thank you.
And how are you dealing with the kernel command line with the OS3 hash that they're actually booting up, like when you're actually seeding the whole system, when you actually do the deployment?
How do
Because traditionally, you would just like append like, for example, if you're using like a loader.conf or something along the line, you would just basically point the OS3 revision that actually want to boot in the NITRD, and then you...
Yeah, so that's where the UKI boot integration works. Like when you mark the thing successfully booted, we launch like UK boot CTL, switch to slot B or mark successful boot B, and that will change a bit in the UKI boot partition, so that next time UKI boot boots, it knows to look at partition B or slot B for the kernel, and the kernel, there's also a symlink that matches the root deploy directory.
Ah, okay, so via symlink then actually find the...
And the initRMFS looks at the, like, here you can, so Android boot always adds this to the booted kernel. So you know what slot you're on, and then you can look at the, just like those three.
So it all works with the assumption that you're dealing with like AB boot slots in a way. Okay.
Because if you're not using the A-boot style integration with OS3, then it would use BLT files.
Yeah.
And that's not really something we can validate against. Those are just lots of complexity.
Yeah, makes sense. Thanks.
Okay, I think that's good. Thanks, Alex. And those, oh, there you go.
HDMI directly. I don't trust the USB-C.
For some machines, we had to switch it to be 1080p.
Okay. Let's see if I have. Should work. It detected something. Okay. It says it's on and it's powered. Okay.
It's detecting it, but not showing up.
Yep. My notebook tells it's on, but
Yeah.
it's not showing up.
Yeah, I think then can you change the resolution? I think it was 1080p is what worked for some of the previous machines. I don't know why it's not detecting it on top. I can also, if you have your slides in the...
The slides are uploaded.
Okay, then we can use mine as backup just to see.
Yeah, that would be fine. Yeah, let's switch.
Okay, let's just try that. Sorry. Oops. And then you'll just have to use the keys here. You can do
Does it have full screen mode?
Oh, yes. Okay. Thanks.
Okay. Yeah. Hello, everyone. My name is Michael, and I will tell you how to use Secure Boot on Rockchip RK3588. And I have technical difficulties. For Secure Boot on RK3588, you have to generate a key, sign your image, burn the hash of the key to your hardware, and that's it. Secure Boot is enabled. Thank you for your attention. I see that I have some time left, so maybe we look a bit closer. I will tell you about how Secure Boot works on RK3588, how to actually sign the firmware image, how to enable Secure Boot, and finish with some recommendations and further resources for reading into it. That's me. Secure Boot or Verify Boot is a set of verification processes designed to ensure the integrity and legitimacy of the firmware running on a device. I stole that definition from the Rockchip Secure Boot Developer Guide. So, for Secure Boot, we have some image. In this case, I have a Rockchip image with a key in it, a signature on that, and a bootloader inside. The SoC during boot, it runs in boot ROM. For Secure Boot, it reads the hash, we mentioned it before, from Secure OTP. That's e-fuses that you burn once, and then you can't change them anymore. On RK3588, these are only accessible from the Secure World or EL3. Details don't matter, but that will be important later on. It compares the hash in the OTP area with hash over the public key that's contained in the image. Use that public key to verify the signature of the image. Use a hash in the header to verify the bootloader and execute the actual bootloader. We can't do anything about this. So everything we have here is in the boot ROM provided by Rockchip, and we don't have a chance to change it. We have to trust the boot ROM. We have to trust the OTP that it's really writable only once and that it's not changeable during boot. What we can change is how we get the key, the signature, and the hash into the OTP area. So in the factory or on your build server, you have a key pair, and from there you take the public key and put it into the image and use the private key to sign the image. The thing that has to be secret in this case is the private key you see in purple on the slides. And you have to somehow get the hash of the public key into your device. That's also something that you have to do in a secure environment. So it has to happen in your factory. You have to have full control over this step. Otherwise, someone may change and write some different hash into your device, and secure boot is broken. First, let's look into how image signing works. Of course, Rockchip provides a downstream solution for that. It uses MKImage to generate the firmware image, and then you get the RK-Sign tool, which generates the key pair and allows you to sign an image. This approach is supported by Rockchip, of course, but this RK-Sign tool is binary only, so we don't know what's going on in there. We may trust it, we are not sure. The RK-Sign tool is also a bit clumsy to use, so you run it several times, and in the background it generates a configuration file, so that's not something that's easy to integrate into your build tools or your build chain. And I'm personally not sure if the RK-Sign tool supports HSM support, so I saw a few hints, but I never was able to actually work with some HSM. So that's a question. With Barebox, we use OpenSSL to generate the key pair. I think we can kind of trust OpenSSL to actually provide proper keys. And Barebox provides an open source tool, RKImage, which generates the image, and in the same step, it also signs the image. So once you build Barebox with a configuration for secure boot, you will get your final image already signed. The advantage here is all the tools are open source, so you can look at the source code, modify it if necessary, and build it yourself. The RKImage tool supports PKCS11 for talking to any HSM that provides this interface for retrieving your private key, so you can use that to get better security on your private keys and move it out of a build infrastructure. The disadvantage is it's not supported by Rockchip. If that's a disadvantage or an advantage, I don't know. You have to decide. And it may lack features that are provided by Rockchip. I'm not sure if there is anything missing from RKImage. I implemented what I needed and ignored all the other features. You may need more or something that's provided by Rockchip. For the board lockdown, the downstream solution, I told you OTP access is only possible from the secure world or EL3. So in U-Boot, U-Boot needs to write the hash in the early boot. It retrieves the key from the device tree. So you put your device public key into the device tree, and during boot, U-Boot calculates the hash on this public key, and it writes the hash into the OTP area. Problem with that is you require a separate image that carries the public key in the device tree for your device bootstrapping. That's something you can do, but in this case, you have a separate image in your factory that you have to manage. And because the OTP is not accessible from the normal world or other exception levels, you can't check if your board has secure boot enabled or which hash is written into the OTP area. So you have no information if secure boot is actually on. In Barebox, the lockdown works slightly different. You calculate the hash on your build machine. So the public key hash is something, it can be public, so you can carry it around. You just you have to ensure the integrity of this hash, but that's a different issue. And on the device, in Barebox, you have a separate command that you can run, give it this hash, and it will enable secure boot. So you can use at runtime a command to enable secure boot on your devices. And since the OTP area is not accessible from the normal world, it has to go through Opti, and Opti will write the hash, actually write the hash to OTP. So there are two parts in that. One in Barebox for talking to Opti and as a user interface, and an Opti PTA to actually enable a secure boot on the device. This approach needs scripts during your manufacturing. So at one step in your manufacturing, you run your system, check secure boot is not enabled, then run the command with your hash, enable secure boot, and after that, only secure boot will be enabled. You have the advantage to be able to exactly determine when this will happen during your manufacturing. So you can do stuff before, enable secure boot, and do stuff afterwards. That's your responsibility here. And the second part is you need Opti support with the RK Secure PTA. You need an upstream Opti for that. So it won't work with the Opti provided by Rockchip. So to come back to the first slide, you use OpenSSL to generate the key pair. It's an RSA key. You configure your Barebox build to assign the image with this key, and you enable the RK Secure command to talk to Opti. You build your image. You use this RK OTP script to calculate your key hash. You can pass your key there, or you can also pass an image there, and it will extract the public key and give you the hash for that. And you boot Barebox and run the RK Secure command, and secure boot will be enabled. Some recommendations. Store your private signing keys on HSM. The secure module. No question about that. If you enable secure boot, check your public root key hash before you program it into your device. You will have a brick otherwise. And because of that, you want to test on expandable hardware first. So if you only have one device on your desk, I wouldn't try to enable secure boot there. And after you enable secure boot, you would want to test if unsigned images or images that are signed with a different key are rejected. So to be really sure that secure boot is enabled. A few further resources. The GitHub repository by Dual Tachyon, I don't know how to pronounce that. They did a lot of reverse engineering, so everything I know about secure boot on RK3588, I know from that repository, and I worked on building it into the upstream projects to make it useful or usable. Another resource is the Rockchip Developer Guide. It will partly document what's happening in the earliest secure boot, and it will also talk about how Rockchip recommends to sign Linux or sign the rootfs and have the secure boot continuing after your bootloader loaded. I didn't cover that because that's something once you have a trusted bootloader running, you can decide how to continue further in your boot chain and ensure secure boot there. The documentation of Barebox documents the process how to enable secure boot. So what I told you in this talk, you can find in the documentation as well in smaller steps and what to enable and how to enable it. And you can find the RK Secure PTA in upstream OptiOS in this repository. So in the latest Opti releases, you already have the PTA that's necessary for secure boot. Of course. So now actually, thank you. If you have any questions, meet me later in the evening because we won't have time for questions here. If you have questions about my design decisions, I'm very welcome to hear about that. If you want to implement that in U-Boot, also talk to me. I have an implementation for Barebox, but not in U-Boot. If you want to implement that in U-Boot, come to me, and see you today in the evening. Thank you.
So, do we? You want to walk around a bit? Maybe. How do you turn it on? You know what? I'll turn it on if I need to walk around. Just leave it. It's fine. Okay, we can start. I introduce myself, I guess. Yeah. Alrighty. Test, test. Okay. So, hello everyone. Welcome. My name is Marek Vasur, and today I'm going to talk about U-Boot on the boot core as an always-on debug tool. First of all, thank you very much to Renesas Electronics Corporation. The content in this talk has been developed on sponsorship from this company. Thank you very much. Next thing, let's get to the talk. The talk will have 4 steps, 4 parts. First will be motivation. I'll show you what it is that has been making me not very happy and how I addressed that. Then the second part will be porting of U-Boot to Cortex-M33. Finally, I'll show you some example usage of the resulting stuff, and then we'll wrap it up and move to the next talk. The talk actually contains an Easter egg. If you can spot it, then good for you. It means that you would work for a very long time if you managed that. Motivation, let's start with that. I'll make 2 assumptions in this talk. I'll be talking about an ARM SoC. That means I'll be using the ARM terminology extensively. However, anything which is in this talk is very much generic. You can use it on MIPS, you can use it on RISC-V, you can use it on any ISA pretty much whatsoever. Also, if you ever have this kind of a side access to your running system, you cannot put this in deployment. So this is all meant for development purposes. If you are debugging something, if you are working on the system, you are not supposed to put this kind of stuff into production. Now, what has been bothering me for a while? You see, like when you have an embedded system and you power it on, it will start some sort of a core, a core, and it will boot the bootloader, and then it will boot the Linux kernel and reach user space. But throughout the course of this, bad things can happen. Bootloader fails to boot, or Linux kernel fails to boot, or Linux kernel actually boots, but you want to look at some register. Or the user space boots, but you want to poke around without disturbing the user space. These kinds of things. And you may say, okay, let's use devmem if you are in Linux. Just run devmem and figure out what the value of the register is. But that register can be protected, say, by trust zone. And then you cannot access it. Or you really don't want to tamper with the system at all because it's been running for a month and you do not want to copy anything there, or you just cannot reboot it or whatnot. Or the kernel doesn't boot at all, and you get no log output whatsoever. And you say, okay, now I would like to read the kernel console and I would like to figure out what's going on. But you can't because it's stuck. And these things, they have been bothering me for a while. So I was thinking, yeah, it would be so super cool if I had some other piece of silicon in there, in that SoC, which would be running on the side and which I could just activate and start poking around into the system from the side and figure out what's going on. Read the register, check what's in the DRAM, this kind of stuff. And actually, it happened because the contemporary SoCs, they nowadays no longer boot from the A cores directly, but instead, they have a boot core, which is something else. It could be an M core, it could be something else. In my case, it was an M core, and the M core has been setting up the SoC, and only then, when the SoC was fully set up, that means when clock, power domain, resets were fully configured, DRAM was fully configured, only then did it load U-boot into DRAM and TFA and OptiOS and started the A core, which just entered the TFA and booted from there on, which is super nice. And besides that, the M core, when it finished its job, it just set itself into some sort of a low power state. So it really only did the initialization and then it was doing nothing more. I was thinking, yeah, okay, what would happen if we were to put U-boot on this boot core, which also has like full access to the system, and we made U-boot shell available on this boot core? Then what I could do is I can literally use U-boot shell in all of its tools, scriptability, memory accessors, maybe even TFTP loading, to explore the behavior of the main A core when I need it. It would just be always there. And this is what I set to do. I picked a specific SoC, which is the Renesas RCAR Generation 5 X5H SoC. This one is very capable. It has many cores. One of them is the boot core, which is called the RSIP core, Secure IP, Renesas Secure IP. It's Cortex M33 with 2 megabytes of SRAM, which is very convenient because we can run U-boot in these 2 megabytes of SRAM, and we do not have to run U-boot in DRAM and disturb the main system. Awesome. It also has a dedicated core for SCP, System Control Processor, which runs an SCMI server. It has RT cores, Cortex R52, and it has A720 cores, the application cores. Now, another benefit of this is that for the application cores, U-boot port is fully upstream as of 2026-04, and so is TFA at the upcoming TFA 215. So we can just fill in the Cortex-M specifics and be done with it. The boot flow of this particular SoC is very much what I outlined. That means the SoC powers up, it runs through bootrom, the bootrom runs on the RSIP core, then the bootrom loads up to 2 megabytes of content from Hyperflash into the SRAM and starts executing that on the RSIP core, which is the Cortex M33. The code which runs on the RSIP core initializes clock, power domains, reset, it initializes DRAM, and then it starts the SCP core, which it loads with SCP firmware, and then starts the A cores, which run TFA, OptiOS, and U-boot from DRAM. That's what it does. And I decided to replace the original software with U-boot on this device. So let's talk about porting U-boot to Cortex-M33. Before we go into the details, I would like to also point out that there are differences between Cortex-A and Cortex-M. I would like to list them briefly here. We will not talk about any Cortex-A which is older than ARMv6, because this is history, but the ARMv7A, this is interesting because this is ARM and thumb instruction set, dual instruction set core, and ARMv7A is interesting, correction. ARMv8A is interesting because this is ARC64 core. This is what we have on the A side. On the R and M side, it gets a little bit more confusing. The ARMv7R looks very much like the 7A, but the V7M looks also like the V7A, but it doesn't have the ARM instruction set, it's thumb only. Now the V8M is like the V7M. It's still thumb only. And it's still ARC32. That means we will be using toolchain, which can be also used to compile stuff for ARMv7A for the Cortex-M33. That's convenient because the toolchain is also available in Debian, it's available in regular distros, and it's been there for a while. Oh, and ARMv7R, that looks like the V8M. But of course, these cores have details which you need to look at. Now, the M33 in particular, it also has its own specifics. It's ARC32, that means like V7A, but without the ARM stuff. It's thumb only. It has split instruction and data bus. This is a bit of a challenge there because the core can execute instructions from one location, and it can read from the same location, but it cannot write data there. And in reverse, with the other bus, it's a location where the core can read and write data from, but it cannot execute instructions from there. The core has TCM, tightly coupled memory. This is super convenient because we can put stack in there, and it's a memory which is very close to the core. That's why access to this memory is very quick. And finally, it has memory protection unit, MPU instead of an MMU, to set up memory area attributes like cacheability. So this core doesn't have any MMU tables. Instead, it has a bunch of registers which you program with memory attributes. That's the difference. Finally, the Renesas RCIP version of the Cortex-M33. For our purposes, it is Cortex-M33. It has a bunch of other IPs which are there, but they're of no interest to us in this case. Now, porting U-boot to the Cortex-M33 it's kind of a mix of big topics. I listed a few on this slide. The first two are very important. That means data-only relocation to handle this split instruction and data access, and then DMA remapping. These two things we have to really dig into. The rest of it is kind of the usual U-boot porting topics. That means hardware initialization code, coexistence between U-boot port for 32-bit and 64-bit core, special drivers for bare metal access, remote prog, and so on. I'll go through these topics. It's going to be me jumping from one thing to another, so please bear with me a little when I go through all these things. I would like to talk about the split text and data bus first, and I actually have a picture here how it looks like, because it should be easier to understand this way. So the M33 CPU is sitting there on top on the picture, and it has a view of memory which is in the middle. Right, let's see, right here. Yeah, cool, you can see that. Oh. It can access instructions through the C-bus. It can read the memory which is accessible through the C-bus, and it can execute instructions from this. But it can also read and write into the same memory through the S-bus It cannot write into the C bus. Whatever is written through the C bus, that gets discarded. But if you want to write into memory, you have to go through the S bus, which is in a different memory location for this core. Right, but you cannot execute instructions from the S bus. So that's the limitation. It's actually a security design baked into the core, that's why it's there. Now, both the C bus and S bus access is actually mapped to the same SRAM here. But with U-boot, what we need to do is when U-boot is executing, it may write into its own binary because there are some variables in there. And these variables may be accessed via what's called an indirect access. That means the U-boot code looks, right, something like this. Essentially, in the binary, there is a load instruction, which is not directly loading any data from an offset, but it's loading actually a memory address within the binary at which there are some data. What we have to do during regular U-boot relocation is we have to place U-boot at the end of the DRAM. Now, I think I should go through the U-boot relocation first, show you how that works, and then I'll get back to the data-only relocation, to the handling of this kind of a split configuration. Problem with this is that when U-boot is executing and wants to write its own applications, it is executing through the, wants to write its own variables, which are in the binary, it goes through the C bus only. And it will try to write into the memory locations in the C bus, which obviously will get discarded. So writes into U-boot's internal variables in the binary will just not happen. The solution is to patch the U-boot binary at runtime and make sure that writes into these internal variables actually go through the S bus. And this kind of patching is implemented in a similar way that U-boot relocation works by default on regular U-boot, not on Cortex-M. Now, relocation of U-boot in case of the regular relocation works in such a way that U-boot binary is actually copied to the very end of the RAM, and then there is a fix-up stage, and then the U-boot relocation code jumps to the end of the RAM and starts executing the relocated U-boot from the end of the RAM. In case of this split text and data access, we do actually a very similar thing. We also do a fix-up stage, but we do it slightly differently. So in case of the regular U-boot relocation, it works in such a way that the fix-up stage iterates over a section which is called rel-din. That section contains pointers into the original pre-relocation U-boot binary, and it's pointers to every single point in the pre-relocation U-boot binary which contains some sort of an address which is used in indirect loads. So what we do during relocation, during the fix-up stage, is we go through this section, we look up every single one of these pointers, and then we increment the address of the pointer so that we would actually get a pointer into the relocated binary. And in that address in the relocated binary, we read the address which is on the memory location, incremented by the relocation offset, and then write it back. And then finally, we can jump onto the relocated U-boot binary and start executing it. For the split text and data behavior of the Cortex-M33, we can do something similar, except we will not copy any U-boot binary at all, because we already have the U-boot binary here in the SRAM, and it's accessible both through the C bus and the S bus. So for this setup, what we have to do is we only have to go through the rel-din section and update every single entry which actually lands in the data section so that it goes through the data bus. The way it works is that we use a relocation offset, which is essentially delta between the C bus access and the S bus access, and we patch all the locations in the U-boot binary through the already relocated address, or, well, not really relocated address, but in the data RV area. This way, when U-boot is then running from the location after this relocation fix-up, which didn't really copy the U-boot binary, it will be using variables via indirect loads, which are in the data RV area here. Okay, this is called data-only relocation. The code is already upstream, and it picks up on the U-boot relocation. It's really just a slight tweak to it. The other problem with this split text and data bus is that DMA buffers, which U-boot may be writing, is using addresses now in the data RV area here. But the DMA has a different view of this area here. So when U-boot is actually writing a DMable buffer, which is in the SRAM, it has to write it through the data RV area, and the pointer addresses of these DMA buffers, which U-boot sees, are actually different addresses than pointer addresses which the DMA controller has to have programmed into its own registers. So we have to calculate some sort of a remapping of the addresses of the U-boot DMA buffers before we program them into the DMA controller registers. This kind of a remapping is described in device tree using DMA ranges property. And the DMA ranges property basically says that the CPUs, which are on the parent bus here, if they access a memory range, which is this one, this one, of this length, then that kind of access gets remapped to the child bus here, and the DMA controller will see that access on that address. That means if the CPU is writing through the data RV port into an address 0xb blah blah blah, that's the data RV, the DMA controller has to pick up the same data from an address 0x0 blah 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 because of the remapping. This is all already supported in U-boot. This is part of the U-boot core code. The only thing which had to be patched were drivers, which do actually DMA and which were not yet aware of this remapping. They had to be extended with a function which recalculates correctly the DMA addresses. And with that, we were able to do DMA on the M33. So there is that. There is other couple of things which I'll now go through quickly. Early hardware initialization. The M-Core is essentially the first thing which runs software on the platform. So it does a lot of register poking, configuring AXI bus priorities, these kinds of things. It doesn't really fit into the U-boot driver model. That is why this has to be done in the early initialization code, in board files, or architecture initialization code, and this is how we did it. Another thing is drivers. So the U-boot port for the ARCAR X5H already existed for the A-cores, but on the A-core, the enablement of clock, reset, PINMUX, power domains, I'm sorry, not PINMUX, ignore that. Clock, reset, and power domains has been done via SCMI. So the U-boot that was running on the A-core was communicating with the SCP, which was running on the SCP core, and talking SCMI to it to enable whatever it needed. Now, on the RCIP core, on the Cortex M33, which is the boot core, we do not have this available because the boot core is responsible for starting the SCP core. And that's why the boot core has to have drivers which are kind of dual purpose, which do direct access in case the U-boot is built for the boot core. And they also do SCMI communication in case the U-boot is built for the A-cores. And right now, these drivers have just a kind of a big if-def in them. They reuse some of the structures, but otherwise it's either or. This may be improved in the future. Another thing is coexistence of the 32-bit and 64-bit U-boot ports in the same code base, essentially using the same files. For the most part, in here, it's kind of a no-brainer, that's no issue, but there were a few sections of the code which had to be somehow conditionally compiled. What we did is, as best as possible, use is-enabled or config is-enabled macros. These are the preferred macros in U-Boot because they allow compiler coverage, compiler test coverage. The way it works is that the code is actually compiled, and then the compiler figures out that the code is not needed, so it optimizes it out, but at least the compiler does analysis on the code. But some of the code really has to be if-def'd out fully with hash if-def. We couldn't get around to that part. Right. Next thing, usage of OF upstream and Linux DTs and so on. So the ArcRX5H has an initial device tree in the Linux kernel now, and U-Boot is importing Linux kernel device trees into its own tree with every Linux kernel major release. That means right now it's going to be 6.19, 7.0, 7.1, and so on. These device trees from Linux are actually available to be used as U-Boot control DT as well if the U-Boot port enables config OF upstream configuration option. And this is preferred because then the delta between U-Boot device trees and Linux device trees is shrinking, which is desired. I mean, device tree is a hardware description, so it should describe one hardware always. Now, the ArcArgent 4 has been switched to OF upstream recently. That means like a week ago. But the Cortex-M33 support in the ArcArgent 5, that one still lives in a U-Boot specific device tree. However, the U-Boot specific device tree for the M33 looks like this. It effectively includes the original Linux device tree and does nothing else. There are, however, U-Boot differences, both for the Cortex-A port and for the Cortex-M port. These are in the -U-Boot DTSI extras. These are differences which, in case of the A core, add nodes which are not yet in the Linux kernel. That's Ethernet. In case of the M core, we disable eMMC at minimum because we do not want it on the M core. Another thing, LMB. This is a software protection mechanism, software memory protection mechanism for U-Boot. It works roughly in this way that U-Boot marks some memory areas as do not access, and then when U-Boot commands would potentially try to access these memory areas, that access is blocked. There can be other properties of these memory areas, but roughly this is how the software memory protection mechanism works. It works also in the other way that we can mark certain memory areas as, yes, these can be used, this is memory actually. And we do make use of this LMB. We mark the DRAM access window on the Cortex-M33 as, yes, this is memory, because we want to be able to TFTP boot into it and load stuff from UFS into it. So we have to do this kind of trick. Otherwise, the Cortex-M33 port is not aware of any DRAM, and it is not using any DRAM. It's running entirely from the SRAM. One more thing, remote proc. Right, so the U-Boot for the M33 is responsible for bringing up all the other cores. That means the SCP core, which is the SCMI server then, and also the A cores. For that, we use standard remote proc driver, which is integrated in the U-Boot driver model. This is no issue there. It is accessible via the rproc command, just like that. The remote proc driver is doing a little bit of a trick enablement of the cores. It is capable of starting the SCP core directly by poking the hardware and releasing it from reset. The A cores and R cores, they are not started via direct hardware access because the code is very complicated. Instead, we allow U-Boot to spin up the SCP core, which then contains the SCMI server, and then we use the SCMI server to start all the other cores. So we avoid duplicating all that code in U-Boot. Now, I've been going from one topic to another. I would like to put it all together here. Basically, what all this ad hoc jumping from this topic to that topic all over the place led to was the ability of U-Boot to boot on Cortex-M33, go through the initialization, bring up the clocks, power domains, resets, pinmux, DRAM, and so on, and ultimately reach the U-Boot shell. in the U-boot shell, there is then a default boot command which is being executed. The default boot command looks like this, and it does the following. It initializes SCSI, which is backed by UFS storage. It initializes remote proc, loads the SCP processor, then loads a bunch of stuff from the UFS, which is TFA, OptiOS U-boot, and it starts the SCP processor, and it starts the A-cores. Ultimately, in the end, you get U-boot on the A-core after all this happens. And after all this happens, U-boot drops into the U-boot shell. That's it. That's where it all led to, the ability to run the default boot command, which looks like this, and which gives you the full flexibility to fiddle with the U-boot on the M-core. Now, I would like to show you a couple of examples, how the U-boot on the M-core looks like and what you can do with this. The possibilities when you have U-boot shell, they are effectively endless. You can do all kinds of loading. You don't necessarily have to load only the SCP and then TFA, OptiOS, and U-boot, but you can load other things in other ways from whatever storage you desire. This is great, and actually the M33 has network access, so you can start bootloaders from network on the A-core, which is super convenient. If you are doing bootloader development, you just drop it into your TFTP route and then let the machine boot the bootloaders. The other thing is you get full observation capabilities. You can read memory, write memory, read registers, write registers. There is no access restriction from the M-core to whatever the A-core is doing. Super cool. The one thing which is a little inconvenient, but you have to deal with, is that the M-core should have its own UART, because otherwise the UART output would interfere with the Linux UART console. That's the only thing which you should be aware of when you do these kinds of things. Here is actually one example of how it looks like. This is U-boot running on the Cortex-M33, and it's really unsurprising. Here it's just regular U-boot, no real surprises there. You can see it has 2 megabytes of DRAM, which is actually the SRAM. It has Ethernet access, and here it is actually doing some loading. This is the execution of the default boot command, and this is where the U-boot on the M-core just started U-boot on the A-cores. That's what it did. And then at the end, line 28, I am writing some sort of a magic number into a memory location from the M-core. This, by the way, this magic number is not picked randomly. This is the U-boot magic number, which you can see at the beginning of your images. This is the other side. This is on the A-cores. So you can see at the very beginning, here, SCP is booting, TFA is booting, U-boot is booting, okay. And then the A-core can read the same DRAM, and the magic number is there. Okay. This may be a little boring. Next thing, loading bootloader components from network. So I showed you that there is some sort of a default boot command in the Cortex-M U-boot port, but it can be adjusted. Instead of loading from Hyperflash, we can load SCP from network with TFTP, just like that. And then we simply start it. In this case, I'm loading the SCP into DRAM and then loading it into the STCM of the SCP controller, and then I start the SCP anyway. We can actually load everything from network, just like this, and then start the whole bootloader stack. We can even load Linux vidimage from network, from the M-core, just put it into DRAM, and then let the A-cores boot this. It looks like this on the Cortex-M, as you can see it here. It loads the SCP and so on, then starts the remote processors, just like that. And then on the A-cores, SCP starts, TFA starts, U-boot starts, and it can boot the Linux kernel. The important thing about this is that if you are doing any sort of bootloader debugging, being able to load the bootloader from network instead of having to fiddle with something and installing it somewhere, this is just great. Now, there is one other thing which I would like to show you, which is pstore and ramoops. This is a slightly different thing. The thing is, when you boot the Linux kernel on the A core, it could be that it will not print any output. And there is a functionality in the Linux kernel, which is called ramoops. It's part of the pstore subsystem, where if you enable config pstore and define this kind of a reserved memory node, the Linux kernel will place its kernel console and other metadata at this well-defined location in DRAM. Now, the U-boot on the M33 and U-boot in general has the ability to actually parse the pstore and extract data out of it. So even if your Linux kernel doesn't boot, if it actually placed something in the pstore, the U-boot on the M33 can read it out and implement and interpret it. And there's a pstore command for this. You basically use pstore set to point U-boot on the M33 to the pstore location, and then say pstore display console, and it will dump the Linux kernel console out of the memory location of the A core. So like that. Now, I'm through my slides. I would like to wrap it up. What can I say? If you have a U-boot running on the M core right next to your A core, it's versatile debug aid. You can poke registers, read memory. It's excellent if you can boot bootloaders from network. This is awesome for bootloader development. The one thing which I'm actually missing in this case is GDB ability. This would be very nice if we had this, but I'm not sure if the hardware will allow me to do this. So yeah, that's it. Thank you for your attention and questions.
Hi, thanks for the talk. Are there ways to access memory above 4 gigabytes from the M core?
This is an excellent question, which I actually wanted to answer in my slides, and I had no chance because I forgot about it. Thanks for that question. Yes, we can access memory above 4 gigabytes. The M core itself has a remap window, which allows pieces of the interconnect to be mapped into a specific location of the M core address space. And then you basically program the window, select what it is that you want in this window, and the addresses will be remapped that way. Yes, hardware has support for this.
So what is the speed of the M core? So how fast can we peak? Because I assume the A cores poke a lot faster than that.
Yeah, sure, the A core is way faster. But what's the question?
The question is, what's the ratio between peak and poke?
Ooh.
Roughly.
I do not know what the exact frequency of the M core is right now.
10, 100, 1,000, roughly? I have an idea.
20, I think. This would be my guess.
That's pretty good.
20 or 30,
okay.
I think. But I mean, it's not exactly practical comparison, because when we load the bigger blobs from the UFS, we use DMA. And it's the same DMA that the A core would be using. So it's not like we are doing a lot of memory copying or anything which would be CPU core heavy. Oh, I see. Register changing. That means generation of interconnect requests. That I do not know, but I can have a look at that. Because it doesn't depend only on the CPU core frequency, it also depends on the interconnect behavior. The interconnect, I believe, is a regular AXI. That's why I would have to have a look at that.
Hi, thank you for the talk. Just a curiosity, what's the intended usage of this RSIP? Because I don't think the Renesas put it there to do U-boot peak. So I was wondering why not using a single core for the RSIP and the SCMI server, like in other platforms?
Hey, they call it the Renesas Secure IP, and that's the main purpose of this. So in deployment, you are supposed to use this for secure boot. Essentially, this core is responsible for authentication of everything else on the platform.
Okay,
And
so you can use...
in deployment, you are not supposed to be running U-boot shell on this. This is for development purposes only, this.
Okay, so let's say at runtime you can use it for example, crypto operations and so on normally. Theoretically, at least.
Can you please repeat that?
At runtime on a, let's say, production system, you can use it for auxiliary crypto operations, for example, like let's say an HSM or something. Theoretically, at least. I am thinking, for example, I'm use it to, for example, NXP platforms.
Let's talk about this after the talk, because I didn't really understand the question. I'm sorry about this. Just grab me after the talk and we'll talk about it.
Sure. Thank you.
Sorry, yeah.
There's one more here.
So as Marek said, it's for booting securely. I don't. It's not really used for runtime support of whatever.
Wolfram, can you interpret the question for me, please?
So as I understood it, it was like, what is this core used? And as you said, it's used for secure boot. I think the assumption what it can be used at runtime in Linux for offloading cryptographic something. No. But that's not what it's for. It's for ensuring...
That I believe is not the intended use case, but I'm not 100% sure of this.
I agree, but I agree that the intended use case is to start secure boot, the secure boot chain.
That's correct. It's the root of trust, effectively, but a programmable one.
Okay, thanks, Mark.
Thank you. Okay, we're going to do one more lightning talk, and then we'll have a quick break.
Yeah, we'll try it. Oh, come back here, that's what I wanted. I want to extend this way, yes. All right, we're ready. I'm talking about watching your scope. This is something I want to talk about, the scope guard macros and some things you can fall into that I've noticed recently, even very experienced kernel maintainers making the same mistake. So I saw it enough times that I said, hey, let's talk about this. Quick introduction, I'm David Lechner. You might see me around the internet as DLEC, not so much on social media, but in the technical places. I've been working for Bay Libre for close to 3 years now. And fun fact, I got my start in embedded software. Everything I needed to know about embedded software I learned from playing with Lego robots. About 10, 12 years ago, I started upstreaming patches for the Lego Mindstorm ZV3 in the kernel, and that's how I got introduced to the kernel community, the U-boot community. And these days, as one of my side projects, we're now working on a thing we call PyBricks. That's a full open source stack for Lego programmable hubs, old and new, to keep software running up on them as Lego retires products, try to keep them out of the landfill as long as we can. But back to this talk, what are we covering? So I'll talk about what is automatic cleanup stuff in the first place, how it got in the kernel, and then we're going to look at the pitfalls that can trip you up, and then I'll give you my opinions on some of the things maybe we can do about them. Here's the quick history lesson. We're talking about a concept called resource acquisition as initialization. I think that term came from C++ originally. Other programming languages have it. Some have like keywords built in. The first time I really internalized this concept is when I was learning the Go programming language and learning about the defer keyword, that the idea there is, for example, if you're opening a file, you say something equals open my file handle, and then the very next statement you write is supposed to be a defer, close that file statement. So that, and all of these things kind of work the same, that where you're declaring your variable, initializing your variable, and allocating your resources all done in the same statement. And the scope of that lifetime of the resource and the variable is all limited to the scope of your function, or maybe a smaller scope within a function. And whenever that variable is going out of scope, that resource is automatically being freed. So we've had this in the Linux kernel now since about mid-2003. It's in the cleanup.h header, and it's kind of built out of some fundamental pieces. The _free macro is like the very fundamental building block, that this is what we use to have the C compiler attribute that ties the callback function that does the cleanup to whatever variable we're declaring. And then one of the most common ones you'll see in the kernel is the guard macro that's used for managing lifetimes of any kind of lock that we don't want escaping the scope of a function. Always make sure we release our lock before we return. And then Quire is a new one that's actually been introduced just this year that's works a little different. It's for conditional locks in the kernel. So that's kind of the big picture. So let's look at where you can fall in the traps. If you recognize that video game, you're at least as old as I am, or you're a retro gamer. So I'm a reviewer in the IO subsystem, by the way, and in the IO subsystem, we use a lot of switch statements. So the first one I wanted to point out is that the guard macro and some of the other macros similar to it is actually declaring a local variable. That's not obvious when you see it in macro form. It looks like a function. And the Clang compiler does not like it when you declare a local variable inside the case block of a switch statement. And so it'll give you this nice compiler error, which if you haven't seen this before, it's kind of hard to understand what this compiler error means, but it's just telling you that you can't declare a local variable there. And there's a quick and easy fix for it, that if you just add braces to add a scope, then that contains the variable declared by that guard macro within that scope. And so that makes the compiler happy. That one's an easy fix. The rest aren't so easy, so I'll be saving them to the last section of what to do about it. The next section is scope guard. This is the title of the talk. This is the one that I saw happening a lot that inspired me to come up here in the first place, that the scope guard macro is actually implemented using a for loop. So if you see this in the kernel, it's totally not obvious there's this for loop because it doesn't say for anywhere in the macro. And so you might be surprised when you try to use a break or continue out of the scoped guard. When you have an outer loop, it's actually breaking out of the scoped guard block, not out of the outer loop. So I found, when I started noticing this, I went through the whole kernel and looked and found like 4 different bugs where people had, like this one, where people had introduced a patch that used scoped guard and didn't know this, and introduced a bug or a change in program flow unintentionally. Like in this one, somebody decided that this section of code needs to be protected. It has the continue statement in it. They put a scoped guard around it, and well, now this continue is breaking out of the scoped guard scope instead of out of the outer for loop. So the con guard function at the end of this function now is always getting executed, where before the continue was skipping that. And when I reported this bug on the mailing list, I got a reply from Mark Zigner that gave me a nice quote for this, that he's been bitten by this too. It's not just me that's noticing this. But he said his strategy was to just make a mental note to never do this, but of course that's a brutal strategy, so that's why I'm up here to try to get more feedback on what's a different strategy we can use. And then, I don't want to talk about scope conditional guard. I'm a terrible singer, but imagine that to the tune of, we don't talk about Bruno from Disney's Encanto movie. So it has all the problems we know and love from scoped guard because it's a scope loop. And then on top of that, you can see there's a return statement right in the middle of the macro arguments. So it's not very clear at all, like what the program flow is of when is it going to return, when is it not. And another thing I've noticed in there that I don't think most people have noticed is that it's actually ignoring the return value of whatever the is acquiring the lock. So some of these are Booleans, doesn't matter, but some actually return more than one error value, so we'd be losing information if we're ignoring that error return. And yeah, there's a link to one of the bugs I found with that. And this is the inside. This is not even like the full macro expansion. This is the very abridged version. And yeah, it's scary, so we don't want to talk about it. So those are the pitfalls I've noticed. So now on to what should we do about it? Of course, there's lots of opinions on these things, so this is according to me. First one is the free macro that we talked about. Since we're doing the RAII pattern, we're supposed to be doing the declaration, initialization variable all in the same place. I know all of us in the kernel are trained to do like the C89 style, where you do all of your variable declarations at the beginning of a function, then code later, but there's actually an exception for this one that it's okay to declare the variable later, and we actually want to do that because it can lead to bugs. There's a link about that if you're interested in more. And I know we said we aren't going to talk about scope conditional guard, but we have the acquire macro now, which fixes all of the problems with that, so don't be tempted to use it, just use acquire now. In fact, scope conditional guard was so bad, we ripped it out of the IIO subsystem even before we had the acquire replacement. And I looked, there's only like 20 files left in the kernel that still use scope conditional guard, so yeah, maybe we should just rip it out completely since we have something better now. And if you enjoy popcorn threads, you can read about the one time that I tried to fix scope conditional guard, and what I did was not very technically good, but somehow it got accepted into the kernel anyway, went all the way to Linus, he saw it, grumpy emails ensued, you know how that goes. So what should we do about scope conditional guard? There's lots of different approaches we could take, different ideas we can do, so yeah, I'm hoping to hear feedback from people of what do you think is going to be best, what works, what doesn't. If I ruled the world, I would probably just avoid it mostly, that instead of using that, if we want to break out of a loop, break out of a conditional guard, then I would write it like this, where it's obviously that we have a do-while loop that we're breaking out of rather than hiding that for loop. I forgot to mention earlier that there's actually a few places in the kernel, like especially the input subsystem and in the sound drivers, where people have seen that you can break out of the for loop like that, and so they're actually breaking out of it, so that makes it obvious. Unless you already know what's going on, that code's not so obvious. But I do make one concession that the one-liner scoped guard is pretty handy. It's better looking than having braces like that. Oh, and yeah, this is the one place in the whole kernel where somebody actually put a comment on the break to make it obvious that this is breaking out of the scoped guard and not the for loop. So if nothing else, maybe we could put comments everywhere else, and enough people will see it, will kind of get used to this is the way it works. And one more fun one, another place where someone wanted to use scoped conditional guard, but they also wanted to use a continue statement, and they couldn't. So they had to write it kind of funny like this. So that's all I've got to say about that. So open it up for questions.
Any questions before break time?
There's another one, another interesting issue of scoped guard, which is not that terrible. It's just that it causes warnings when you have a scoped guard where you assign a value to a variable and you define that variable but not initialize it at the top of the function. It will think that it can actually use an uninitialized variable. So like if you use it later. So something like an attribute saying like this loop always runs at least once would be in order, but
yeah, there was a problem like that before, that when we used it a lot in the IOSO system, we would do early returns and switch statements, and the compiler couldn't figure out that the loop only ran once, but somebody came in a while back and made the macro even scarier to fix that. So I don't know if that still exists or if that's something you've seen more recently.
I wasn't aware.
Maybe it's fixed.
I think you made an interesting suggestion on stage, which was not on the slides. You said that scope guard didn't include for. Maybe we should call it for scoped guard or something.
Yeah.
Okay, let's thank David again and go to the break. So now we have a break. We'll be back in 30 minutes, so come back at 4:15. We'll have a couple more talks, and then we'll be off to the evening social events. Check, check. Okay. Welcome back, everybody. I hope you got a little something to eat and drink. Stretch your legs a little bit. We're going to have a couple more talks and then get off to our evening party at the beach. I'll pass it over to Yao to continue on.
Thank you. Hey, everyone. My name is João, and I'm going to talk a little bit about the lessons I learned shipping real-time AI and embedded Linux as a new system integrator. A little bit about me. Oh, there we go. Oh, okay, you're not happy. Okay. A little bit about me. I'm 20 years old. I'm a field application engineer at Toradex. Differently from most people here, I'm kind of new to the industry. I only have 1.5 years of experience, but I do have 10 years experience getting electrocuted by 12 volts. I love old cars, camping, and collecting soldering iron scars in my hands, soldering all kinds of things. And I'm currently finishing my computer engineering degree at Facamp in Brazil. About this talk a little bit, this is not a benchmark on what to do at all. This is about the decisions and trade-offs I did during a personal project that evolved into something way bigger than I expected, and everything that broke during that development, and everything I learned from it. If you ever said it works on my machine and you deployed something in hardware and it broke, this is the talk for you. So how this project started, last year I was doing my internship at Toradex, and my boss told me that I had to do a demo with our hardware. I also was starting my college thesis, so I joined everything together and started doing a project with everything together. It started as a simple project on the M62 and migrated to the IMX 8M Plus, and I decided to do something about motorsports. I love cars, I love racing, I love the smell of burnt rubber, drifting cars, and I decided that the smart path here was to do the obvious, the proven, and the responsible engineering path and extend the scope of doing a gigantic project that I couldn't handle in a month. And so, oh, there we go, again. So what is the project? So I decided to do a real-time vehicle telemetry system for sports racing. The idea is that I collect GPS, accelerometers, Hall sensors, engine data, and feed everything into a system. I do a machine learning assistant track positioning and drive pattern detection, and transform the Speeduino, which is an electronic injection system for the Arduino, into a microprocessor from Toradex, and do a full ECU replacement. So simple project, weekend, you could do it. And yeah, so the use case here would be pretty much amateur and semi-pro motorsport. The idea originated from doing track days and deciding that I could not afford any pro solutions that are out there in the market. The idea is that like the solutions for people that are starting or amateurs in the area and don't now have $5,000 to spend on the solutions out there. So the system started pretty simple. So the whole idea here is that I collect data, so GPS, accelerometer, throttle position, brake position, steering, gearbox position. I process that data, I filter it, I do a timestamp and sync it, I do a simple packaging and I classify it, and then I give a user response for whenever he's oversteering, so whenever the car is turning more than you expected, understeering for when the car is turning less than you expected, and off track, when you go off track. And the system repeats ad infinitum. But I had a data problem. So every session was around 30 minutes, and I was collecting hundreds and hundreds of megabytes of data, sensor data, unfiltered. The GPS was at 10 hertz, the accelerometer was at 30, the CAN line was full of sensors everywhere, and everything was simultaneous. And I decided, well, I might as well ship it to the cloud and process it there. It's definitely gonna be easier that way. And it kind of was. The first setup was pretty easy. The machine learning part was, well, the usual of most projects there. The real problem here was latency. I was facing pretty much 2-3 seconds of latency at best scenario here. And that was not ideal, especially when you're driving a car and you want to go fast. 2-3 seconds here really matter. And that's the difference of doing the best lap in your race and the worst lap in your race. And exactly what I said. So latency was putting the driver there on a reactive mode. And most circuits, especially in Brazil, 4G and 5G data is not reliable and not guaranteed at all. Not even for reliable circuits in when you consider rally or other modes of the sport. And a system that depends on that network that you don't control is definitely a liability, and you would get fails from that. And then I decided, well, I'll just throw everything on a system on module and see what we can do. I decided to run inference, detect anomalies, and deliver feedback with no connectivity whatsoever, and using local hardware. And yes, I was able to do it somehow. Yeah, so again, as I said, I decided to use the i.MX 8M+, pretty powerful SON, quad core, all the good stuff there, so don't need to go into details here. Good NPU, so, and asterisk, it was free for me, so. Yeah, so where the data that I used came from. I did around 60 laps in a local circuit back at home. So 45 laps around for clean racing and 555 for all the events that I mentioned. I collected GPU traces, accelerometer readings, all the inputs, and engine and gearbox information directly from the electronics from the car and the sensors I installed. Just an FYI, doing electronics in a car from the 90s is not fun, so there's that. I did labeling derived on heuristic detectors, so the oversteer, understeer, and off-track events that I did, and the data set was inherently balanced. Again, most of the laps I did were clean, and critical events were rare by definition. It's hard to replicate some of this stuff, and flagging them was even harder. So I had to do some oversampling and weighted loss. Especially because collecting all that data is definitely expensive. Running a car for 60 laps is not cheap. Okay, so the pipeline is pretty much straightforward. I did some training with PyTorch and sklearn offline on my computer. I ended up exporting only for TF-Lite. This is a little bit outdated, but for a portable format. I did some quantization from FP32 to Int8, specifically for latency reasons, and deployed on the module that I was using. So for quantization, I started as an FP32 module specifically for accuracy. Again, I didn't have a lot of points of data to start there, and doing a more precise model was ideal. However, because of the NPU on the i.MX 8M+, you cannot use FP32. You had to migrate to an Int8, so I had to quantize for that type of data. The map weights and activations from FP32 to Int8 gave me a 4 times reduction, give or take. Gave me a lower memory bandwidth and faster arithmetic for the course. I tried 2 main approaches: post-training quantization, which was fast and didn't require any retraining, obviously for the post-training. But accuracy was dependent on the data itself, and quantization-aware training, where the model learns to tolerate reduced precision during training. It was better accuracy, but it costed more doing a once-time training. For the post-training calibration data set, it must represent the full distribution of real inputs, and the domain-specific small models are kind of disproportionately sensitive for quantization error, especially because of the large general models, and validation is not optional here. I had to validate a lot here and do a lot of remodeling. Some of the results that I have, especially for the normal driving and common events, the post-training was acceptable. It drops just 0.02 on normal driving. And for events, it started degrading significantly. I saw reductions from 0.83 to 0.62 in the F1 scores, so some major decline there. And the QAT recovers almost all that gap, specifically for the quantization-aware training it did. Latency on the CPU itself, both methods had some latency, obviously, but I'm sorry. I saw some, especially using the bigger model, I saw latency of around 115 milliseconds, which dropped with the smaller module to around 30, especially on the A cores on the CPU. And you could see the difference in the graph, and you could see that after the training, both of them were kind of relatively the same for latency, so no major changes there. However, However, for NPU, I saw a reduction about over 60% for both models on running on the NPU on the 8M Plus. For the post-training quantization, I saw a drop from 32 to 13 milliseconds, and for the QAT, I saw it from 30 to 12, proving that the NPU is the way to go here, and running these models, it's a big win on the NPU. The model had to be quantized before deployment to Int8, and every operator in your model has NPU support, and if it doesn't, it just will fall back to the CPU. Here is just some of the memory footprint for every packet of data that I saw. You can see a little bit better here. So the quantization was, without the quantization in FE32, each package produced around 30 megabytes of data. That's at around 5 hertz during operations of the module. So you could see how that would stack up really significantly during use. And you could see that using the Int8, it would drop significantly, just an increase with the NPU because of the driver package that the NPU uses. The system is not running alone, however, so that memory usage is it's significant. But well, everybody here knows how to run inference models and just do simple machine learning modules on their hardware. That's not hard. It's a controlled environment. It's a module that most people know how to use it. So yeah, we solved the easy part here. The hard part for me was shipping the complete product. The model was maybe around 20% of what needed to be done, and the other 80%, so kernel drivers, runtime compatibility, memory management, thermal behavior, containerization, OTA updates. It's what happens after the product needs to be shipped. So yeah, what production means on embedded Linux is pretty much just your lab demo runs with you watching, and the second you need something else, it will break. A product is pretty much a production system is pretty much something that runs continuously, unattended, in an uncontrolled environment for an entire period of time. In my case, an engine bay at around 80 degrees Celsius for an entire session, which was around 20 to 40 minutes, give or take, every time. The failures are different, the design requirements are different, the debugging is different. A product is very different from it is on the table when you're testing things. Everything that follows here is the gap that I experienced between developing that product and testing it on the field. So, for the major things that broke on my system, and probably will at yours if you're doing something similar, is the kernel drivers and user space runtime alignment using NPU, the accelerator operator support gaps, memory pressure under sustained workloads, and thermal behavior doing continuous inference. So, about the kernel and runtime alignment, the NPU on the 8M Plus is exposed to a kernel driver. The TF-Lite delegate, it offloads to the NPU, and if you're gonna, I'm sorry. Okay. So the TF-Lite delegates offload all these operations to the NPU. It's dependent on drivers having some specific interfaces. And if your kernel version and the NPU delegate version are not aligned, this infers that it will fall back to the CPU, which will increase your latency and your processing time. And for my case, that was not an option. I had the whole system here had from start to collecting data to showing results to the user had a latency of around 200 milliseconds using NPU. When it fell to the CPU using the NPU, yeah, when it fell to the CPU, I saw an increase to up to 2 seconds during that whole system. So that was something that I broke my head multiple times. And the moment you update one and without the other, it tends to break things, and the alignment shows itself as a problem. So for your sanity, update everything together or not at all. Long-term support solutions definitely are your friend here. Okay, so about the accelerator operator support. So the NPU itself does not support every operator available for TF Lite. Operators who know that don't have the implementation on the NPU will fall back to the CPU and will fall back in the same problem that I mentioned. The latency increases, the solution doesn't work as it should, and you end up having problems. So how to fix it? You redesign every layer as to use a supported operator, or you accept the fallback. In my case, I spent a solid weekend developing some of the operators that I needed to use specifically with support for the NPU and the AM+, and it was pain, I'm not gonna lie. And well, yeah, never assume full NPU coverage. Check your documentation. I guess it's something that we all learn in this industry, and optimize later. For memory pressure, every inference after quantizing for int 8 was around 10 megs. So that on itself is not a memory problem. The problem is that like after 15,000 consecutive inferences after a whole session, with acquisition threads, buffers, container runtimes for all the sensors that were running, and Horizon OS all competing for the same limited RAM, that tends to be a problem. So I designed the system to design against fragmentation, which will be repeated small allocations and deallocations from activation buffers fragments over time. Buffer growth, so ring buffers for session data that were coded to be explicitly bounded, and unbounded growth consuming available RAM in sessions longer than its test duration. And container overhead, so each container had its own memory namespace, running inference and acquisition separate to the containers itself. A mitigation for this will be also to pre-allocate inference buffers at startup and using some fixed size ring buffers for eviction policies on the data. And yeah, try not to kill your MMC logging everything. Ask me how I know. For table behavior, aside from what it is here, the 8M Plus, from what I learned, tends to be running way hotter than some of the other NXP modules. But that in itself is not a problem. The thing is that I was running on a temperature ambient that easily exceeded 60 degrees Celsius before the SOM itself even started generating any heat. And I saw the CPUs running from 70 to 85 degrees during the whole session. I saw some throttling, around 80% drop and 10% increase in latency, but honestly, I'll consider those numbers acceptable. And 3 design considerations to keep in mind here. Mount with airflow consideration. This is something that I learned the hard way after trying the second module that I was testing with. Log your temperatures continuously during development. Again, careful with the eMMC because you will destroy that thing, logging everything. And set your thermal trip points explicitly on your device tree. Thermal management here is not only a mechanical problem. Be a friend to your local mechanical engineer and improve your performance in software and airflow. They will thank you for that later. So yeah, I mentioned Horizon OS a little bit. This is the part that I do a little bit of marketing, but Horizon OS is our open source software with a focus for embedded Linux. It's a container runtime with focus in container runtime with no package manager. It's a root file system that it's read-only. It's a focus, again, using a Docker container, so with isolation, modularity, and no OS rebuild to update. Over-the-air updates with OS3 and actualizer, so CRA compliant. And for this project, I used it because, well, 1, it's from my company, and 2, I honestly believe in it. It's been working wonders so far, and the lack of headway that it gives us during hardware, it's been magical, to say the least. It runs on pretty much everything now, so Raspberry Pis, Beagle boards, x86, Panasonic microwaves, maybe not the microwaves, but yeah, so. And so yeah, the whole strategy here for developing and deploying the applications was using containers. I'm not gonna explain containers to you guys, everybody here knows Docker, but the 4 areas where containerization for embedded Linux here had some deliberate design was hardware access for containers, separation of sensor ingestion and inference pipelines, reproducible builds, and safe over-the-air updates without refreshing the whole system. The whole container on Linux it doesn't have access by default, and every hardware peripheral, kernel interfaces, device nodes, etc., must be explicitly granted. So about separating sensor ingestion interference, the whole strategy here was I was specifically with the earlier versions of my software, I was facing some major crashes, specifically collecting data from sensors I bought from AliExpress. So I decided to isolate pretty much everything. So from data acquisition, the inference container, the graphical interface for the user, the AI models that I was using, everything was isolated so that if one thing crashes, you can simply restart and redo it again. So specifically for sensor data and ingestion inference, I had two containers, so acquisition and inference, and the communication with them was done with a shared volume. The whole, so as I explained, if it crashes, one can simply restart and do its whole thing. For the over-the-air model, I approached this with a two-layer architecture using Horizon Cloud. The whole idea is that the OS is pretty much separate from the model and the containers itself. So the OS layer will be updated via OS tree using Horizon Cloud, and the model and every other application will be updated with a container image. So the workflow will be pretty much, specifically when retraining and trying new things on track, was pretty much new weights for the model, fine-tuning it, exporting it, building a new container image, pushing to registry, and pushing to Horizon Cloud. So this way I wouldn't have to build a new Yocto image every time I had to rebuild these things. I had also a rollback philosophy. I broke a lot of things during this process. I think I had a solid 20 or 25 versions of this. So I had started doing a rollback philosophy here, keeping earlier containers image tagged and pinned. My Docker profile is a mess, and I have to clean it up after this presentation. So yeah, version it, sign it, and deploy it the same way you would any other kernel update. So obviously the demo and the project itself always have a gap. Everything in the stock worked at some point in isolation, and everything in the stock also broke at some point as a system. A product for me at the end of the day is what happens when those things run simultaneously, unattended, in real conditions, and for the whole duration of the session. Repeatedly. And the gap between it works and it ships is where most projects stall. From experiencing this whole project, the big major things that broke were the NPU's fallback, with especially the silent ones. So whenever I hit operators that weren't supported or didn't know it was supported, the CPU would get a full load, the system would crash, the data would be lost, and latency would increase in a major way. So I only knew this because I logged everything and measured everything, and instrumenting everything from day one was something that saved my ass multiple times. Kernel and runtime diversion drift. I had some problems with versioning for a lot of the dependencies I used, and especially with TF-Lite. Especially in updating TF-Lite without the BSP or vice versa broke NPU delegation silently multiple times. So I decided to keep one atomic dependency all the way, and I won't update anything ever again. Thermal one ray, especially on the final laps during track, I did not optimize the system for thermals at the start of the day. My software was messy. The casing was simply just a metal box in the engine bay, so it got hot real quick. So I had to proper optimize these for real scenarios, and it made my life so much easier. Unbounded ring buffers. So the memory grew slowly but consistently to the point that I killed the EMC multiple times. So at the end of the day, I killed 4 modules. Don't tell my boss, but it was a learning experience. And container permission. I discovered that running containers without permissions can complicate your life really seriously. And the interfaces were not accessible whenever I deployed them in the field as they were when I tested them in the lab. So what scales from this? Specifically training and quantizing the module itself. Choosing the right modules and strategy to use is very important. I took this as a learning experience for most cases, and you tested a lot of modules. For me, the quantize aware training costs way more during the initial training, but it gave me way better results down the line. It's a cost that I paid once, and the accuracy gain was significant. I used a multiple container architecture, and that's obviously scalable, so separation of the process made life so much easier, especially when things crashes. The over-the-air updates, so the update discipline that I set up early made my life very much easier down the line. Having thing breaks because it didn't choose the right dependency and not having to build the whole system because of this was definitely humbling. And the telemetry pipeline structure itself, so having everything timestamped, synchronized, and consolidated package made debugging way more easier. And well, lessons learned here. So choosing the quantize method as a systems decision is something that I'll keep doing down the line. Choosing something that you pay once instead of ever use is definitely something way helpful here. The NPU is definitely conditional, so int 8 only for 8 and plus. Check documentation and check operator coverage. The kernel and the runtime must be aligned. Containerize for isolation, so separate everything. If one thing breaks, I just want to keep that thing broken. Logging is not optional. Not having that data to analyze later is definitely something that will bite you down the line. And treat the model as a firmware itself. So version it, pin it, deploy with discipline, and design it for rollbacks, because you will definitely need it down the line. And yeah, thank you.
Awesome talk. So you mentioned that you were looking to replace like a multi-$1,000 all-in-one telemetry system. What would you say your bill of materials would have been at the end for your complete solution, as it were?
With the module itself, I'm sitting at around $500.
Sick. I'm not throwing that far.
The architecture of your solution reminds me Erlang language. Don't you think about it, using like everything written in Erlang instead of?
I'm sorry, could you repeat the question? I didn't get it.
Your structure, your design reminds me about Erlang language, programming language, where the idea, the paradigm is like if thread is dying, that let it die and restart again. So have you considered to use Erlang?
No, really. To be honest, I never even heard of it before.
Did you use Etnaviv driver and Mesa for the NPU, or did you use the proprietary stuff from NXP?
I used the proprietary from NXP. Again, this was a first-time experience with as NPU usage for me, so I took it as a learning experience. And specifically for documentation, I used to be in the documentation team at Toradex, so I decided that using the proprietary hardware from NXP itself and doing the black box scenario here would be ideal, because I was doing all of the documentation for it for Toradex. So,
look at Etnaviv, please. Look at Etnaviv and Mesa, please. It supports the NPU on IMX8M+.
I'm sorry, could you repeat it? I couldn't hear you properly.
Etnaviv, Mesa, it supports the NPU on IMX8M+.
Oh yeah, I explored it a little bit, and it's something that I plan to migrate it to down the line. But again, not a lot of experience using it so far.
So, you mentioned thermal management. So what are the exact cooling measures that you're taking on that system, like passive and active?
It's mostly passive. The system itself doesn't come with any active cooling, especially from Toradex. And it's pretty much just an air vent coming from the outside. I just drilled a hole in the car, pretty much.
Then it's okay. So then that's more active cooling, I guess, because passive would be like reducing heat. But anyway, so do you have passive measures in the sense of like CPU frequency throttling or idle states? Or?
I do have some. I implemented some throttling, but at the end of the day, the performance at around the max heat, so which was around 85 degrees, wasn't significant enough that that I had to like do anything more drastic. It has some throttling, but nothing major. Something from the CPU itself.
Okay.
So I didn't code it anything explicitly at the end of the day.
Okay.
Any more questions? Thought I saw one more. No. Well, we have a talk tomorrow on the open source NPU drivers from Tomio, so we'll get more information on that tomorrow.
A follow-up question. Did the hole that you made in the car affect aerodynamic properties?
Well, to be fair, it is a $500 car. So I have not measured it, to be honest.
But do you consider it to be an issue when scaling, since there was, or like more serious applications? Will there have to be a trade-off between cooling and aerodynamics?
For a more professional solution, for sure. This car started as a 24 hours of Lemons build. Again, cheap car. So the whole idea here was to use as little resources as possible. I wish I had access to a wind tunnel to tell you how much the impact is, but again, a little bit hard.
Okay, thank you very much. That was a great talk.
Yes.
Ouais, ça marche.
All right, so I'm told we should get started, even though it's a bit earlier than what the schedule says, but we have quite a lot. So we initially wanted to share war stories, but we came to realize that there's already enough stories of war in these times. So we came up with a different title, so that's why you see it changed compared to what's in the schedule. So it's going to be Debugging Chronicles. Not sure it's going to be enough to bring us a more peaceful world, but maybe it's going to be helping you come to peace with the bugs that you'll face in the future. So quick intro, but even though I guess most of the people in the room know us, so we're Bootlin, we're an engineering company specialized in embedded Linux and Zephyr, so we do engineering services and trainings. We're a team of 28, and we are really proud to be supporting Embedded Recipes for the second year in a row as a sponsor. So thanks to the team organizing the event and making this really great community-driven event every year. So thank you very much, and a round of applause for them. So the way this talk's gonna work, we have 6 debugging chronicles to share, completely unrelated with each other, kind of random topics. So I have 5 guys from the team here and me. So we'll go through each of them. At some point we might stop, so maybe we won't be covering the 6 of them. It depends on how much you fall asleep and how much you wanna go to the evening event. Because we would probably run over time if we cover the 6 of them, so we'll see. So each time we selected a story that we found was quite interesting, where we struggled a bit with something, and there's a little bit of a technical kind of takeaway that we took from the story. And so without further ado, we'll start with the first of them with my colleague Romain.
So, okay, is this, okay. I'm Romain, hello, and I mainly do kernel driver development at Bootlin, so I've seen quite a lot of kernel bugs, and, well, I like resolving kernel bugs a lot because it feels a lot like detective work, and just like with detective cases, some of them are more memorable than others, and I wanted to share with you a particularly memorable one, which is networking related. So, let's get in the details right away because we don't have a lot of time. We had a customer which had a product, an embedded product based on an SoC from TI. So this is some, but it's a typo. It's supposed to be a SoC. It's an AM437X from Texas Instruments. And one of the particularities of this SoC compared to other vendors' platforms is that you have something called the PRU, the Programmable Real-Time Unit. And this is basically a set of co-processors, so special purpose cores with their own custom ISA, which you can use to emulate different types of IP blocks. So you can emulate serial port controllers, Ethernet controllers, etc. And you do this by running pre-built binary firmware from TI on the PRU cores, which are compiled for this specific use case. So for example, in this case, our customer was running the Ethernet EMAC firmware on the PRU cores. And this customer was reporting that they were seeing some malformed Ethernet packets on the link. So we'll see the details a bit in the next slides. But basically what this meant here is that when you sent a packet over a certain size, you had a repeated instance of truncated packets with wrong Ethernet checksums at the end of the packet, well, frame more like, before the actual correct frame was sent in its entirety. So here's just a view of the overall packet processing chain in hardware. So we have the Cortex-A9 here. This SoC has a single Cortex-A9 core. This will run Linux and your application stack, and it will send the packets, well, stuff them into a packet queue, a FIFO, implemented using a ring buffer. And then the PRU takes care of the rest. So basically, it's going to drain the packet queue progressively, and then stuff them into its own TX FIFO, byte by byte. And then this gets sent out to the layer 1 hardware, so the Ethernet PHY over an MII link. One thing to note here is that once you start sending a frame, you have to keep sending bytes over the MII link until the packet is done, until the frame is done, right? Because there is no storage on the right side of this diagram. The PHY will not store anything, so if you stop sending bytes, then you have issues. This is why we have this second TX FIFO here. Does this actually work? No, it doesn't, anyway. So, at the beginning, the first thing that we did, as always, is try to reproduce the issue. We managed to do this without too many problems.
And characterizing this, it turns out that above a certain size, the frames would get resent in truncated forms, just like I previously described. And I'm going to gloss over a lot of details here, but basically we ruled out with initial investigation, we ruled out a bug in the kernel Ethernet driver, which was the main suspect at the beginning. And so the packets received by the driver were correct, the frames that were placed in the packet queue were correct, and we didn't see anything strange in how the PRU was consuming the packets in the ring buffer. So then the only possibility left, apart from like a hardware bug, was a bug in the PRU firmware itself. And this is where things get interested. Usually this is when things get painful because firmware issues are notoriously difficult to troubleshoot when you don't have the sources. But in this case, and this was really unexpected, we actually did find the sources of the TI PRU firmware, which was a very, very nice surprise. They're published by TI in a repo called TI PDK, like Processor SDK. They're written in assembler, so it's PRU assembler, written for the specific ISA of the PRU cores. And so using this, we were able to actually rebuild a PRU firmware Ethernet image, which behaved like the pre-built one that we had originally. And then next up, the next step was to set up some tracing methods because obviously you didn't have PrintK, like the PRU cores have no access to the serial hardware or anything. So what I did was like write small assembler routines to instrument the code, and these would just write like 2 unused bytes somewhere in the shared RAM. It was pretty cramped, and so this allowed us to like see, well, basically to place trace points. Oh, and on the right side, we have a diagram that is straight from the documentation of the PRU firmware, and this is something that also really positively surprised me. That not only was the source code available, but it was very well documented, very well commented, and there was high-level documentation about the overall flow of the program in the PRU. So this made my life so much easier when I was troubleshooting this. And eventually, I managed to track down a place where the firmware wasn't behaving quite as expected. And this was, well, obviously the transmission path. This could already be kind of expected. And specifically, we were seeing some TX50 overflow events. And it turns out that the issue was in the part of the firmware that computed the fill level of this small TX50 on the right side that you see here. And the way this is done, well, I won't go into too much detail, but basically what happens is that there is no way for the PRU firmware to know, to like directly measure the level at which the packet FIFO is currently filled, and it needs to monitor this closely. Why? Because as I mentioned previously, once you start sending a frame, you have to keep a steady stream of bytes going on the MII link until the frame is done. So for this, you need to make sure you don't underflow or overflow the FIFO. And how does the PRU firmware compute this if it can directly measure the fill level? It does this using timestamps. So at the start of the frame, it takes a timestamp, and then whenever it wants to measure the fill level, it takes a second timestamp, infers a duration since the start of the frame. Then it divides by a number which depends on the frequency at which the bytes will be sent on the MIL link, and this is known at compile time. And using this, well, it just subtracts this by the number of bytes that it's already pushed into the FIFO, and that allows it to know the fill level. And the issue here, and the source of the bug, was that this second timestamp, which has to be taken whenever it wants to measure a fill level, this was not taken, but it wasn't actually written to the proper register before calling the fill level procedure. And so this means that instead of using the correct timestamp value, it used just whatever garbage was in that register before the procedure was called, which means that the FIFO fill level was almost always incorrectly computed, and so it would regularly detect spuriously, like underflows and overflows, and whenever it did that, it would basically trigger some end-of-frame events in the FIFO, which would send those malformed packets out on the link. And so this was the fix, well, the fix that I formulated. Later we discussed it with the TI PRE firmware team, and we just adjusted some details. But basically, the only thing which needed to be done here was to load the timestamp from the IAP, so the IP which gives you those time measurements, and load it into the proper register at the right time. And this solved the issue with the malformed packets. And so what's the takeaway here? So we informed the customer, we discussed with the PRE firmware team, who are very reactive on this, and so they integrated the fix. Now it should be, well, this was towards the end of 2024, so it should have been in the PRE firmware sources for a long time now. But so the takeaway here is not that, oh, there's a bug in the there was a bug in the TI PRE firmware, because let's be honest, every firmware has bugs, we just haven't found all of them yet. The takeaway here is that by providing proper documentation for your firmware and providing, well, even better, having an open source firmware, like in this case, you are greatly facilitating the life of your customers, and you're allowing them to make the most of your hardware. I've had similar issues with closed source Wi-Fi firmware, and what took like 1 week to troubleshoot here took literal months, where you had to go back and forth with like the manufacturer, the firmware manufacturer support, send them logs, get patched firmware binaries back, send them more logs, etc. So yes, I think that's the lesson that needs to be learned here. And I'll let my colleague Thomas, well, more my boss.
Thank you. I guess one of the common conclusions of many of these Daybreak Chronicles is that the fix is usually one line, and that first one is a good example of that. So on my side, I'm gonna present you a stupid hack that bites you back. I was not the only person involved in debugging that. My colleague Hervé, who is in the room somewhere here, also Ernst and Alexis, perhaps looking at us on the live stream. He's not at the conference. So we had a customer, yet another customer story, of course, who had an IMX6 system on module. And that customer was already a customer of us, comes to us and says, our SOM vendor has been shipping to us new SOMs on which they changed the Ethernet PHY because of supply issues. And that's the only thing that's different. But they tell us those new SOMs that have a different Ethernet PHY are 2 times slower than the previous SOMs. So it was like, what the fuck? It makes no sense. But the customer tells us the ones with the new PHY are slower than the other one. And when I mean slower, it's not the Ethernet performance, but just like the CPU performance, they run applications, and everything is 2 times slower. Okay? But then the customer comes back to us and says, well, in the end, it turns out that we found old SOMs with the old PHY that also exhibit the same 2x performance penalty. So we're like, okay, at least this is a little bit less crazy. There's no relationship with the Ethernet PHY being swapped. But initially, the bug report was a bit weird. So the customer sends us fast and slow system and modules, and the fun begins. And so we run a very simple CPU-bound application. We can get rid of all the customer application stuff, build something really simple, run it, and it's indeed like 2x slower. Not exactly 2x, it's like 2x-ish slower, a little bit over than 2x slower. And on the older SOMs, indeed, it's two times faster. Okay. So what is using the CPU, right? So top comes to the rescue, doesn't show anything suspicious, like no other process is obviously hogging the CPU. So if nothing is hogging the CPU, is the CPU running at a lower frequency? Is like CPU freq broken or whatever? But CPU freq seems to be configured, working correctly. You switch to the performance governor, makes no difference. So it's not like a CPU frequency issue, at least apparently. So there must be something else hogging the CPU. Interrupts, perhaps. So watch -n1 cat proc interrupts. And indeed, we had one interrupt line with like tens of thousands of interrupts per second on the slow SOMs, but not on the fast SOMs. It's like, interesting. That's an important difference, and tens of thousands of interrupts per second could explain why there's little CPU time left for running useful stuff. This interrupt line is a GPIO interrupt. So the schematics, it's this guy here, this GPIO, so RTC interrupt, okay? And it's indeed connected to the interrupt line of the RTC. But it's like, why the heck would we get like tens of thousands of interrupts from this stupid RTC? It makes no sense. You would get one when the alarm rings or something, but that's pretty much it. Should happen, yeah, once in a blue moon, not tens of thousand times per second. So the RTC is hammering us with many, many interrupts per second. And how does that, yeah, as I said, even make sense? So RTC datasheet to the rescue. And the datasheet shows that this interrupt line is not only an interrupt line, but it's kind of mixed with CLK out signal, right? So it can either be an interrupt or some clock generator, right? So yeah, it's just like smells interesting. So perhaps we're not getting hammered by interrupts, but by the clock generator. So that's a good hint, but still like why we have fast and slow ones, right? It still doesn't make sense. We're running the same code on both, same kernel, same DT, same bootloader, same everything, and some are fast, some are slow. So we still haven't found the real thing. But so back to this clock generator. After reset, the following mode is entered, and CLK out is active and emitting a 32 kilohertz signal, so that kind of lines up nicely with like tens of thousands of interrupts per second. Okay, makes sense. But again, why are we getting this clock signal on some of the sums and not on others, even though the hardware design is the same? Okay, so look at the driver for these RTCs, this PCF8523. And the driver does a bunch of stuff, of course, but the probe does something like that. If I have an RQ configured, I do some reg map write. I write 38 to this like TMR blah, blah, blah register. So 38 basically sets bits 3 to 5 to 1, okay? So datasheet again to the rescue. And that basically I don't know if I see my pointer, maybe not. What, right there, you can see 111, CLK out disabled. So basically, the first thing that the driver does when you use the interrupt signal is that it tells the RTC to not emit the CLK out signal. So we should not have that 30K signal hammering us. So what the heck is going on, right? Because it should disable that signal. So let's look at the device tree, and that's the device tree coming from the customer, not from us, right? It does something like this. So it describes the RTC as a subnode of the I2C controller, and it describes, for whatever reason, and we'll see that this is, of course, important, it describes the interrupt as a GPIO key. It's like, okay, what the heck? But no, that explains why it doesn't work, right? Because this piece of code in the driver only gets triggered if you properly describe the RTC interrupt in the RTC node, right? If you do interrupts equal blah, 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 blah. But here it is something completely unrelated. So from the RTC driver perspective, we don't have an interrupt signal connected between the RTC and the SoC. And so it has no reason to shut off the CLK out clock generator. So it makes sense, right? It's why we have this thing. It still doesn't explain why we have it on some, on the new sums, but not on the other ones, right? So we'll have to dig a bit more. So the reason why our customer did that is because they needed that interrupt signal to be a wake-up source, and we had a great talk earlier today about wake-up sources. And the PCF8523 driver didn't support configuring its interrupt signal as a wake-up source. So they used this hack to have like a GPIO keys, which does support enabling that line as a wake-up source. So of course, the correct thing would have been to improve the RTC driver, but they probably didn't know how to do that, so they did that hack, and it worked for them, and we'll see why it worked for them. So that's kind of the hack that bites you back. But of course, in our case, the RTC driver does not disable CLK out, so we get that flood of interrupts. So now, again, we understand why we're flooded on the slow sums, but not why we also have those old sums that are fast. And the thing is that registers on the RTC are battery-backed, right? So it's not every time you boot that you get a fresh state of the system. For everything, yes, except for how the RTC is configured. So what happened is that if one day you boot a kernel that disabled CLK out, clock generator, then forever this sum is working, right? Even if you boot a new kernel that no longer disables CLK out. So initially what happened is that that customer used our original device tree that was properly describing the interrupt line. So it booted that on all its fleets of devices. All the RTCs were configured correctly. And then they deployed that on many units, things worked fine. Then they wanted to use the RTC alarm as a wake-up source. They deployed that. Everything continued to work because that configuration is battery-backed. But for the new ones, of course, it didn't work, right? Caused all the new units to be slow. We confirmed that because if you took a fast unit, so the old ones, you remove the RTC battery, you plug it back in, the RTC is back to its reset state, and it becomes a slow unit, right? So in conclusion, when playing with RTCs, do some tests from a well-known RTC state. We're not really used to, we think that when we reboot, everything is like back to a pristine state, which is mostly correct, except in that very situation. And it took us a little bit of time to think a bit out of the box about that aspect. So like remove the battery, make sure the RTC is really in its reset state. And don't do hacks because they come bite you later. Thank you.
Hello, I'm Luca, and this story is about displaying pictures on a panel, a video panel. So we got contacted by a customer who was developing a product based on IMX93. They already managed to get all peripherals working on their own except for the video panel. So this is the hardware. It's, the IMX93 has a display controller and a bridge inside the SoC, and then there's another bridge outside to convert to dual LVDS because the panel is dual LVDS. So the same panel was working for the customer on another of their products based on x86, so the panel is not by itself broken. First idea, the customer was using a relatively old NXP fork for the kernel based on 6.6, so I considered switching to upstream, but some parts, especially for the DSI host part, were not present yet in the upstream kernel, so couldn't be done easily. However, there were fixes over time after 6.6, especially on the TI driver. But those were not easy to apply because on top of the vendor kernel, there was additionally a huge patch by the customer with all the hacks they had tried to enable the display. So first thing I did was to dismantle this huge patch into individual patches, doing the individual changes, some obviously irrelevant, like logging, some to be clarified, etc. Then I looked at the panel documentation. The timings are, of course, the crucial parameter for a panel. And for this one has actually two sets of timing, one in the datasheet and one in the ADID file, which is shipped on the panel. And that's what the x86 board is using. So I switched the device tree to use the ADID timings, but kept the other ones around just in case for any test. Anyway, I had no image with either of them. So I went to check the basics, the usual things you always need to check first. The clock configuration in the kernel looked correct. The various frequencies looked reasonable. I checked this, tried to check signals with a scope, but it's not super easy because video signals are fast. Like the DSI clocks was just too fast for my scope, so I couldn't see that. But other signals were more quite readable, and they all looked reasonable. I checked PinMux, it's always the PinMux, you know, but not in this case because the DSI pins on the IMX are not muxed. I checked the resets, nothing was held in reset, and I also disabled all power management, just in case to simplify my debugging. Still, I had no video. So I moved to the previous component, the TI bridge. Nicely, this can generate a test pattern. It was not implemented by the driver, but it was a single bit to enable, so I enabled that. But still, I got a black screen. So I moved to DSI Tuner. DSI Tuner is a tool provided by TI. It is able to provide you the set of registers for a given configuration. So it is useful for a bring up. So DSI Tuner is not open source, but it's written in Java, so it's portable, except it's shipped in a Windows MSI installer for Windows only. And the MSI installer requires a very specific version of Java, which can be downloaded only from sun.com, which is now a dead link. Yes. I didn't laugh when this happened, but now I can. So then I took a deep breath and I realized I can just open on my Linux machine, I can open a MSI file with 7-zip and there's a jar file in it. So I just ran it with whatever Java is on my Linux computer and I had the tool running. So this tool requires a lot of parameters, timings, clocks, and many more. So it took quite some time to get all the parameters. I did several attempts, but after a few tries, I got a test pattern working on the panel, which was a great relief. So basically, all the last part of the pipeline was validated. Then I removed the test pattern, and still I got a black screen. So there are other problems to investigate. But before that, the outcome of using DSI Tuner was that I found two issues with the existing code. So I sent 2 patches, which are now upstream, to fix those issues with dual LVDS. I also sent a patch for enabling the test pattern, which is on its way for 7.2. And then I moved to the previous component again, the DSI bridge inside the IMX93. So I read the documentation, I checked all registers, everything looks reasonable. I enabled the test pattern, which was nicely already implemented by the driver, but nothing, still a black screen. So I checked all the clocks again, all the clocks related to pixel clocks were correct with a good precision, and all bus-related clocks were fast enough to not have bottlenecks, so not clear. There was an error bit raised in one of the status bits, suggesting an underrun in getting the data from the previous component, the LCD-IF display controller, but that was not very clear, and I tried to increase the AXI-bus clock, but it didn't work. So I went again back to check all the basics, check all the clocks, because they are very crucial, and many attempts later, out of pure desperation, I removed the line from the board device tree, a line with 4 assigned clock rates, and I got the test pattern from the DSI bridge. So a lot of joy. This additional part of the pipeline was validated, but when I reboot the board, the kernel hung while booting. And I tried multiple reboots, and it started hanging more than half of the time, so totally unacceptable. So I took a deep breath, and then I went to check all the settings which I had removed. So basically, those were changing 2 clocks. One was the NIC media clock, which is basically determine the speed of the bus to access the pixel data from memory. And it was increasing that from 400 to 800 megahertz, so maybe removing a bottleneck. In reality, this was the change that created the kernel hang. So I re-added only this clock rate, and the kernel didn't hang anymore. The other result was the pixel clock was slightly more accurate, but the error was now in the opposite direction. It was slightly slower instead of faster. And that is the change that actually determined the fixing of the panel. And disabling notice pattern, I finally got an image. It may look ugly, but it's the mode test pattern, and when you see that, it's great. Time for cleanups. I had a huge amount of temporary commit attempts, wild stuff, so I removed all of them, logging, hacks done over time, etc. And at the end, the screen was black again. So. But I was wise, because I had removed each hack as an individual commit, so I could easily git bisect and find the relevant commit, which was actually coming from the huge patch by the customer, the one I had dismantled at the beginning in smaller patches. And this patch was basically, as usual, a one-liner. It is disabling burst mode, so it is the TI bridge which is asking to the DSI host to not use burst mode. The reason for this is not yet clear. The TI bridge supports burst mode according to the datasheet, but it was kind of breaking my setup. I'm still in contact with TI to clarify the reason, still to be sorted out. In the meanwhile, another user sent a patch to disable burst mode in order to fix the same problem on a different panel, so maybe there is some pattern here. Maybe just burst mode is just more sophisticated, so more tricky, and highlighting issues more likely. I don't know. At the end of the story, many takeaways. I'd say that the most important is always check the basics, do one step at a time, try to enable one little piece at a time. Test patterns are very useful in this respect, because otherwise you have a very limited observability over a video pipeline that is not working. There are few things that you can check, and a lot of things that will make your screen just black if they are wrong. So do one piece at a time, start from the end of the pipeline, consolidate that, and then move to the previous component. And that's all. Thank you.
Now a DRAM story. It was mostly debugged by Gregory with my support, so I will do the presentation. A bit of context, one of our customers has a product based on the TI J72 SoC. Yes, it's a product for automotive. We implemented Suspend to RAM for this SoC a few years ago, and it works pretty well. But you may have noticed that recently we had a RAM price explosion because of AI, so the customer found a second source of DRAM chips, and he asked us to confirm that Suspend to RAM is still working with this new chip. So normally it should be okay. Inter and exit retention sequences should not be memory dependent. The worst case should be we need a new DDR configuration. But if it's boot, it should suspend and resume. So the customer did the test, the board boots, the board suspend, but crash very early during resume. So before to continue a bit, a few explanations about boot, suspend, and resume sequences. So you have the boot sequence of the G72 SoC. It's a bit complex. So from left to right, you have a Cortex M4, which runs the TIFS, which is the TI security firmware. Then you have a Cortex R5, which at the end run another TI firmware, the device manager. Then you have the Cortex A72, which runs U-boot and then Linux. So boot flow. So you have some ROM code stuff. Then you start from the R5 core with the SPL, which basically configure the DDR, load a bunch of firmwares from the boot media. This bunch of firmware are TFA, Opti, DM firmware, and A72 SPL. So it loads this firmware as the right places and asks TIFS firmware to start the A72 core. So A72 core starts, runs TFA, then Opti, then A72 SPL, which loads U-boot, and then you have your U-boot prompt, and you can start Linux. Suspend pass. So usual stuff in Linux, you trigger your suspend, you run your suspend pass, then you have TFA. At the end of its flow, TFA save its context in DDR and ask DM firmware to set the DDR in self-refresh and ask the PMIC to put the SoC, the SoC in suspend to RAM state. Few things, during suspend to RAM, the SoC is fully off, no I/O retention, so you lose all your context. And as TFA is running in SRAM, you lose all TFA context. That's why we have to save TFA context. Resume pass, mostly the same that boot flow until DDR configuration. So instead of configure DDR, you just run the exit retention sequence. Then you load DM firmware and TFA, and you ask TIFS to start TFA. TFA detects that we are resuming, so it restores its context and jumps to its resume pass, and then you have Linux and so on. So we added a small improvement. During the boot, we do a copy of TFA and DM images in a dedicated LPM memory region in DDR. The idea is to load this copy during resume instead of loading them from the boot media to speed up the resume. So we started to investigate. We look at the memory chip datasheets. We run some kernel mem tests during the boot. We did review retention sequence. Maybe we missed some hard-coded value, but no. We added some debug logs in enter retention sequence, nothing relevant. We did some debug logs in R5SPL, and we get an interesting message starting ATF. So, looks like we are able to start TFA. So we added some debug logs in TFA, but no, A72 core never starts. So something is wrong when we load TFA or when we start the A72 core. Let's talk about how we load and load TFA. So first, you copy your TFA image in SRAM. TFA image is a TFA firmware plus a certificate to authenticate the firmware. So during the boot, we load the firmware from the boot media, and during resume, we load the firmware from the LPM memory regions. Then we call TI secure image post-process to ask TIFS to authenticate the firmware, enable some firewall on the SRAM, and set some processor configuration flags. So let's have a look to TI secure image post-process. We added some debug log, and we finally found the problem. We pass an image size which is equal to 0. So the function returned very early. Why? Because it works previously with the exact same software. Just because the p-size pointer does not point to the TFA size in the LPM memory region, but it points just after the LPM memory region in an unused memory area. And with these new memory chips, we get the value 0. Why does it work with the other boards? Just because other memory chips are by default initialized to FFFFF. So the size is only used by TI secure. Why it works? Just because the size is only used by TI secure image post-process to invalidate some cache lines. So if you use a very high value, it works. We just invalidate too much cache lines. But at the end, it works. And it's what we had. So we fixed the pointer issue. Suspend to ARM is now working. That's awesome. Great news. Customer is happy. But it works only one time. So that's the good point. And it only works one time, and we break overboards because second resume does not work on all the boards. Why? Just because now TI secure image post-process return a new size using the p-size pointer. And we fixed the p-size pointer, so the p-size pointer now points to TFA size in the LPM memory regions. And TI secure image post-process returns the size of the firmware itself. Remember, the TFA image is a firmware plus a certificate, so the function returns you just the size of the firmware. So during the second resume, when you do the copy using the TFA size in the LPM memory region, you only do a partial copy, so authentication failed, and you have a crash. Solution is pretty simple, just use an intermediate value. And quick conclusion, we did some mistake hidden by hardware, and everything is your fault.
Should we get started with the next one? Yeah? Is all right? I think we're going to be late, but we're not late? Okay, great. So mine is called 4 instructions too many. Let's see what happens. The name you could recognize, it's mine, plus my colleague Gregory Clément, who is involved in way too many stories. So one day, wake up, go to the office, and my Mobileye IQ5 board, so finally not TI hardware, it's a MIPS board, and it doesn't boot. I'm not really sure why. It tells me every second, waiting for core 1 to start. So there's something going on here. I don't remember anything I did on the day before. I don't think I did anything with core booting, so it's a surprise for me. So code hasn't changed. I remember some config changes I made on the day before for my dev testing, so maybe that's the reason. So I call that bisecting two configs. So one known one, the upstream one, is working fine, and the other one I've been using that enables networking and some other features to use on the board on my desk. So I bisect, so I bring the crashing one closer to the upstream one. I change every option one after the other to find what's going on. So I land on something, config dynamic ftrace. It's not ftrace support, it's the function tracer support for dynamic calling. So it's what we usually call a function tracer. You know, when you have knobs that are put inside almost every function and you swap them around, and that allows you to trace your function calls. It's all great, but I'm not even using that. I've not patched any function in my kernel code. I've not enabled ftrace, and it still doesn't boot. So something is wrong here, and we need to look into it. Oh yeah, and don't change your .config on the evenings. It's not a great idea. You might land on the next morning with a bug. So what's going on? I don't want to make it look like it was a straight line story, and I just found the issue straight away. So a few leads we followed, or we had hunched at and looked into. First off, of course, the toolchain might be an issue. We are talking about how the code compiles. Maybe there's something going on here where some wrong code is being generated. I'm not too aware of how ftrace works, and I prefer staying ignorant on that side. But we knew we had seen some issues with toolchains, either upstream or there's one that's called Codescape GCC, so it's a fork by MIPS that we got provided. We have two. I tested a few. I tested two Codescape, two upstream, and that didn't change anything. So quick test, unrelated. Let's move on. So yeah, as I said, could we look into ftrace? Yes, we could. Do we want to do it? No, we don't. So let's bisect. I'm pretty sure I already used ftrace in the past on this exact board to debug performance issues. So what I did is find some, from my notes, find some version that was working in the kernel, compile that, try to boot it, and then bisect from one to the other and see where it lands. So it lands on my colleagues' commits, which was nice in a sense because he was sitting 10 meters away from me, and so I could ask him what was going on. He basically had no clue. He didn't touch ftrace in that patch, so we won't go into the patch too much. However, he gave me some nice info. He told me there are some kernel parameters that can be used to modify the boot flow. So the commit adds parallel CPU boot. So what happens? You boot on CPU 0, and then you boot all CPUs one after the other. That's a bit slow, so rather you do it in parallel fashion, and so that's what he implemented. And so we know the fix, the bug appears when you have dynamic ftrace enabled and parallel boot. We tested a few things. So that's the two requirements we need, and 6.16 kernel version. So with some more logs, going a bit quick on this one, we figured out that the CPU we were booting was not the right one. So CPU 0 was booted. It was given to us from our bootloader stage. And then we started booting CPU 3. That's not great, and there's no good reason to do that. You can see the topology on the right side for IQ5 board. CPU 3, it's the VPU, so it's the VPE1 of core 1. VPE is kind of your threads, if you are familiar with x86. So that's not great. We would rather expect to be booting CPU 2 instead. So how do we do parallel CPU booting? Good question. I guess. What we do is we try to know if we are thread aware. That's the first question. And then there's the concept of primary threads. So it's which CPUs you want to boot first. So in our case, it would be 0, 2, 4, and 6. Because you first boot the VPE 0 of all cores, and then you can boot the remaining ones. So you boot up your primary threads using those CPU, HP, bring up mask. Those are macros that do a lot of things, but they put your CPU hopefully in the right state. So you bring up your first batch of CPUs, and then at the end, you do some masking on the CPU mask, and then you bring up the remaining ones, the secondary ones. So we are stuck somewhere in there. So as I said, we tried booting CPU 3. That's nonsensical. It makes no sense. We know we don't want that, and I had my colleague 10 meters away that told me it made no sense. So I knew that was wrong, and so I checked into that, and our primary thread mask was wrong. It pointed to 3, 4, and 5 instead of 0, 2, 4, 6 that we expected. So yeah, that smells like memory corruption here somewhere. And so just for your info, you have a printk format string for CPU masks. There we go. And so of course, we did all that with printk debugging, and it does work, if there were any doubts. So what is being overwritten? That's the mask somewhere in memory. Yeah, I grabbed all of that. It appeared in the commit from my colleague. So that's pretty suspicious. And you can see the tag that is read mostly. So it puts it into a section that is special. We don't really care too much about it, but it's a bit different. Who could it be? Well, we know the dev config we changed is dynamic ftrace, so we look into that code. We had printk everywhere, which I spared you on the slides because I don't have enough space. And we can see that before ftrace didn't arch init inst, not easy to pronounce, the primary mask is right, and afterwards it is wrong. Something is going on. So how does ftrace work? Sadly, we need to figure that out. So that's what it does here. You don't generate the instructions, so your, let's call them jump lines inside all functions. You don't generate them every time. You generate them once, you put them inside a buffer, and then it's a mem copy when you want to enable dynamic ftrace. One of those is called inst lamcount. So it's a buffer that will store MIPS instructions that we will copy and paste around inside our kernel executable code. And so we know how to generate instructions inside the kernel with UASM ILA, LA load address. Let's stop there. So the first one is the big deal. Inst lamcount is U32, and it's sized 2, so it expects 2 instructions. But if we go into this macro here, USMILA, well, you might not read that easily, but I can tell you that it might generate more than 2 instructions. Here you can count up to 6, I believe. There's some edge checking for where the address is located. So we need more than 2 instructions to encode a load address for an address that is too far away from us. And so that was the big deal. We generated too many instructions, and we didn't check what happened. Here, notice your functions. They are called UASMILA. They take your buffer. They take the register values, the address, and they don't give you anything back or don't ask you the size of your buffer. Please never do that inside kernel C code. Please take sizes, at least as argument or as outputs, so that we can detect what's going on. And so, of course, it happened to be that this was shifted into our primary CPU mask and blew everything up. So this was present forever inside the kernel on our platform. It's just that no one noticed because the read mostly section is not used by too many people. What's the upstream fix? We don't have proper one, so yes, we do need more instruction to encode a load address for an address that is too far away. So what we do is disable ftrace if it's ever an issue and we cannot jump to it. So that's what is going on here. It's not the greatest solution. We need to apply a fix further, but at least no one else is getting memory corruption here. Yeah, and we need to insert jump lines. So the only issue is when you are talking about jumps from modules. It's not a big deal when you talk about kernel code space text. That's it for me. Thanks, everyone.
Okay, so I'm already over time. as usual, I would say. So I have a smaller story. It's about audio, right? So we had a customer that took an IMX7 system on module. He wanted to do a public announcement system, so basically in airports or train station or whatever. So the goal there was to basically send audio over the network, and then at the end, obviously, you need something to convert the digital stream to analog, something to speakers and stuff like that, right? So they needed an audio card. So basically, they just added a codec on that. So on their motherboard, they had a PCM3168A from TI, whatever. Doesn't matter too much. Disconnected to SAI2 on the SoC, which is the digital audio interface. And so basically there you have an audio card, you just add support to that. So very easy, we'll see. Yes, so it was more than 10 years ago, right? So it was about in 2015, 2016, something like that. So the vendor kernel was 4.1.15. And on our side, we went for 4.9, which was freshly released. So we wanted to use upstream. So how do you do that? Basically, we add the card description in device tree, and yeah, audio is working. And this is done. Okay. So yeah, audio was working. And at some point in time, I thought, oh, that would be nice if I could play my preferred music of the time. I don't remember what it is, right? It was 10 years ago. So to test, what I did is that basically I used speaker test. Speaker test is super nice because it allows to generate audio without sending an audio file on the board. So when you are debugging, you know, if you have an init-ramfs or something like that, well, it's super nice to not care about which files are in there. So my usual commands are there. So either I will play a sine wave of 440 Hertz, right? That is a pure tone. Or I could also just use a sine wave of 1000 Hertz because the pitch is way higher, and so you hear the difference very easily, right? I'm not a musician, so I need a large difference to know between those two notes. So what's nice also is that if you see there is a -C at the end, so -C will be for 2 channels, -C1, the first -C2 will be for 2 channels, the -C1 will be for 1 channel. So with some ALSA trickery, you can actually output one tone on one channel, another tone on another channel, which will allow you to know whether you are mixing left and right, or maybe that also allows you to know whether you are sending, you know, samples of the stream of one channel to left, for example, and then at some point it gets desynchronized, and then you are sending right to the same channel, stuff like that. This is some kind of things that can happen when you are working with audio. And, well, the analog output was perfectly fine, right? So this is a 440 Hertz sine wave. So that's what I wanted, right? And then I tested with that actual sound file. And it was recognizable, but it was not, you know, perfect. You could really make the sound out and know what this was, but something sounded weird. So let's start to investigate. The format of the audio file samples were exactly the same as what speaker test was generating. The PCM bus data looked fine. Really, well, I went with the oscilloscope there. I had a look at the PCM bus, so you have some clocks and data and stuff like that. So this is serial, very easy to see. But it's not super easy to know what actually goes over the bus because it's somewhat fast. So yeah. So the sine wave tests would suggest that everything was fine. So I went over the codec controls. You have plenty of analog controls on the codec, so I was just playing with them, seeing whether something did change, and no. The audio sound was just the same. And then I was like, oh, okay, there is also another codec on directly on the system on module. So let's test with that. And basically that was the same. So the sine wave was perfectly fine. But if I was playing some really audios, and yeah, you had some kind of distortion, difficult to characterize. And obviously, when you are using an audio card like this, you are using DMA, right? So DMA is there to get samples from user space directly to the digital audio interface FIFO. So basically, the kernel doesn't know about what the data is that is going over there. So you can't inspect that data directly. So it's difficult to debug. So to get more visibility on that FIFO content, I did create a new audio file. And instead of having 440 Hertz sine wave, what I did is that exactly the same, but I did a fade out on it. So basically, it was just tapered like this. And the goal there was to know, okay, to try to understand what was going on the bus and you know, whether this was correct or not. Right? And this was the result. Right? So there you can see, so that's my wave, and it is fading out, right? But well, something is wrong. You can't see there, but basically the interval between each thing is 20 milliseconds. And 20 milliseconds is typically a period of samples. So basically, that will be one DMA transfer. So, well, that is it, right? So the periods are not played in order, but somewhat in order. So that's why you could recognize the music. So the next step was to have a look at the PCM bus, because now I knew what kind of data I would expect on that bus. So with my oscilloscope, I went there and then I had a look at the PCM bus, and I could see that, yeah, it was already interleaved this way on the PCM bus. And then I had a look at the file, which was obviously correct, right? And the user space buffers are also correct. So it was not caused by user space. So something in between user space and the bus was wrong. So obviously, DMA was a culprit there. And the main thing was that, yeah, it is, so DMA is not right, but at the same time, the transfers are happening. They are happening on time, and also they have the correct size, and they run for the proper duration. So if you play a 10-second file, DMA will run for 10 seconds, which is quite surprising, right? So I continue to investigate DMA. So it was i.mx7. So basically, you have firmware for your DMA controller. So that's the SDMA. So I tested multiple SDMA firmwares. I also tested the one that is shipped on the ROM and stuff like that. No luck. So my next try was to backport what I did. So the full board support, I did backport it from 4.9 to 4.1.35. So the vendor kernel was 4.1.15, but I chose a more recent kernel, so .35, and that was fixing the issue. So something broke somewhere. After discussing that, basically there was one commit. So this one, it was long ago, so I don't exactly remember what the exact issue was, but basically that commit was in 4.9, and there was already a fix floating around when I did that for this particular commit. So basically it was about the residue calculation. So when you do DMA transfers for that on audio, basically you know that we will always be transferring the same amount of data. So basically you just ask your DMA controller to always transmit the same data from the same buffer and go over the buffer and go cyclically like this. So you have cyclic channels, which are not your usual channels, and it's mostly on audio. That's not something you will get, for example, for the network or something else. And so when you do that, when you do transfers, sometimes the transfer is not complete, and so you have to calculate the residue, so what's left to be transferred inside your buffer, and that was wrong at that time, and so basically this was fixed later on. Right. So takeaway from this, I'm not using 440 Hertz tone anymore. Because, well, the tone itself was perfectly fine. Why? Because basically each buffer was exactly the same, right? So basically, the DMA was always correct because the end of your curve was always on the exact period boundaries. So basically, it will repeat itself just fine. So now I'm using 441, 444, or 999, just that it will, not always be the same buffer that will be sent. And last thing, so the issues are not always caused by clocks or pin control, which is usually the case. So yeah, that's what I got from this. And thank you.
Thank you very much. I hope you enjoyed the Debugging Chronicles and know Kevin about the evening event.
Yeah, just a final reminder for going to the evening event. You can get there by tram, you can get there by walking, and make sure you bring your badge so you can get in. And we'll see you shortly. Thank you. Oh, and tomorrow we start at 9:30. First talk will be at 9:30, but we'll be open at 8:30 for coffee and talking with and meeting others as well. So see you tonight and or see you tomorrow. Thanks.
Non, ça ne...